Before we begin tonight's journey through the mysteries of the universe, take a deep breath and let your thoughts begin to drift. You're not here to solve problems. You're here to wonder, to explore the questions that have no easy answers, to gently stretch the edge of what your mind can hold. This is not a lecture. This is a quiet meditation on everything we don't know, from the nature of time to the fabric of space, from the whisper of particles to the echo of existence itself. So wherever you are, whether you're lying in bed, curled on the couch, or floating in thought under the stars, comment below and tell us where you're listening from and what time it is where you are. And if you'd like to support more journeys like this, please subscribe and help us reach 100 subscribers. Every question you ask, every moment you listen, brings this quiet space to life. Now close your eyes, slow your breath, and follow me as we step into the first mystery of the night. Chapter 1. What existed before time began? Before the ticking of clocks, before galaxies were spun like glowing dust across an infinite canvas, before light itself had reason to exist, there was what? This is not a simple question. It's the kind of question that lingers long after the lights go out, whispering to you in the darkness. What was there before time? If time had a beginning, then what came before the beginning? And if nothing came before, how can anything begin at all? To begin understanding this question, we must first realize that time, as we experience it, is not a fundamental backdrop like a stage upon which the universe acts. Time is part of the show itself. It's a character born with the universe, entwined with space, forming what physicists call space-time. According to Einstein's theory of general relativity, space and time are one fabric, curved, dynamic, and responsive to matter and energy. Which means there is no before in the traditional sense. When cosmologists speak of the beginning of the universe, the so-called Big Bang, they don't mean an explosion in space. They mean the beginning of space itself. The beginning of time itself. Time did not exist, then suddenly it did. And that to our human minds is almost unbearable to imagine. Because in our world, everything has a before. Every thunderstorm has a gathering of clouds. Every birth has a pregnancy. Every thought has a moment that came just before it. But what if the birth of time was the one moment in existence that had no precursor? It's possible, according to our best theories, that asking what came before time is like asking what's north of the North Pole. The question collapses under its own assumption. There is no north of the North Pole, because the pole is the limit of direction. Likewise, there may be no before the beginning of time, because time itself is the limit of before. But still, we wonder. Some scientists believe that before our universe, there may have been other universes. A great cosmic cycle where time bends in on itself, eternally dying and being reborn. The Big Bounce theory suggests that the universe could collapse and re-expand, forever oscillating between contraction and creation. In this view, time never truly begins, it simply recycles. Others entertain the possibility that our universe emerged from a timeless quantum vacuum. Not a vacuum in the way you imagine, empty and dark, but a sea of fluctuating potential, a churning field of energy with no matter, no time, no space, yet bursting with the raw potential to become all of it. In such a model, what we call nothing might actually be something, an unstable condition from which universes can blossom like flowers in the void. And then there is the idea of quantum tunneling, a concept born in the strange world of quantum mechanics, where particles can leap through barriers, vanish, and reappear. Some models propose that our entire universe tunneled into existence, leaping from a state of non-being into being, not from a place, but from a probability. Can a universe simply appear from nothing? In the quantum world, nothing isn't empty. It's restless, it's alive with uncertainty, and in that chaos, it may be possible for an entire cosmos, space, time, matter, and light to spring forth, uninvited and uncaused, like a thought in the mind of no one. And here's where things become even more surreal. There are theories suggesting that time might not be fundamental at all, that it is emergent, an illusion that arises from deeper, timeless laws. Just as temperature emerges from the random movement of particles, time could emerge from something deeper, something not bound by sequence or duration. In this way of thinking, the universe didn't begin in time, it began with time. There was no ticking clock in the darkness, no countdown to the first spark. Instead, time unfolded as the universe expanded. As dimensions grew, so did the concept of before and after. But in that first fraction of a second, far smaller than anything we can conceive, the laws of physics, as we know them, break down. In that brief flicker, time itself was still figuring out how to exist. And yet, something had to allow it to happen. Could there be a timeless cause, a higher dimensional realm, something beyond space and time, that gave birth to both? Some physicists invoke the idea of the multiverse, a vast, possibly infinite landscape of universes, each with its own laws, its own dimensions, its own birth and death. Perhaps our universe is just one bubble among many, forming in a cosmic foam, endlessly spawning new realities from some deeper, eternal source. In that case, before our universe might simply be another universe. But here lies the haunting beauty. Even if we build machines that reach the edge of time, even if we decode every particle and formula, we may never know what preceded it all, because knowledge itself depends on time. Evidence must persist. Memory must carry forward. But before time, there is no persistence, no cause, no record, no observer. And still, we yearn to understand. Religious and philosophical traditions have also grappled with this mystery. Some see the origin of time as the moment of divine creation, a choice made by a conscious force that exists beyond reason, beyond comprehension. Others suggest that we are asking the wrong question entirely, that the act of questioning imposes human logic on a reality that may not obey it. Even our language struggles. We say before, but that word assumes time. We say created, but that implies a creator and a moment of making. We reach for metaphors, analogies, half-formed mental images, to grasp a truth that may be forever beyond our reach. So what existed before time began? Perhaps nothing. Perhaps something timeless. Perhaps something that doesn't even fit the categories of thing or non-thing. A kind of origin we're not yet evolved to understand. But maybe, just maybe, the question is the answer. Because to ask it is to gaze past the veil of now, to imagine beyond the edges of the possible, to look up at the stars and feel for just a moment how strange and beautiful it is that we exist at all. And in that wondering, we do something extraordinary. We step outside ourselves, we stand on the edge of time, and we listen to silence, to mystery, to the soft heartbeat of the unknown. And though we may never touch what came before, the question itself connects us to something greater. Not just what lies behind us, but what lies beyond. Chapter 2 is the universe conscious.
There's a strange quietness to the night sky, a sense that something vast is watching, yet not speaking. A presence that stretches across galaxies, beyond nebulae, around dying stars and newly born suns, and in that silence, a question lingers, ancient, unprovable, and impossible to ignore. Could the universe itself be conscious? Not just filled with conscious creatures like us, not just the stage where thinking things happen to exist, but consciousness as a property of the cosmos itself, woven into its very structure, like light or gravity or time. It's a question older than science, yet one science is only now beginning to approach. Not with certainty,
but with curiosity, with mathematical models, with open minds. You see, for centuries we imagined the universe as a machine, cold, objective, clockwork. Galaxies spinning like gears, atoms bouncing like billiard balls, minds merely illusions produced by neurons, and consciousness, whatever that is, reduced to a strange side effect, a chemical byproduct of evolution. But that view is beginning to change. Because the more we explore the mind, the more elusive it becomes. We can map the brain, we can measure its waves, its synapses, its rhythms, but no scan has yet found the feeling of thought. No microscope has discovered the place where experience itself lives. And so we are left with mystery. Where does awareness come from? Some scientists believe consciousness arises only when enough complexity is present, that when neurons or any information processing units reach a critical level of integration, a new property emerges, the ability to feel. But others ask, what if it doesn't emerge? What if it was always there? What if the universe at its most basic level is not only matter and energy, but also experience? This is the foundation of an idea called panpsychism, a word that sounds strange at first, but all it means is this: that consciousness is not something rare but something universal, something intrinsic to reality itself. Not that every rock has thoughts, not that every atom makes decisions, but that even the smallest particles might possess a spark of subjectivity, some whisper of what it's like to be. And as those particles form more complex systems, molecules, cells, organisms, that whisper might grow louder, until it becomes what we call a mind. In this view, consciousness is not an emergent phenomenon, but a fundamental one, not a product of the universe, but a feature of it, much like space, much like time, much like mass. It's a theory with ancient roots. Philosophers from India, Greece, and many indigenous traditions have long imagined a cosmos that is not dead, but alive, not empty, but aware. A divine intelligence that does not sit outside the universe, but within it, But today, even some physicists and neuroscientists are beginning to reconsider. They point to the integrated information theory, a mathematical attempt to measure consciousness by how deeply information is connected and shared within a system. The theory suggests that consciousness is not tied to a specific material, but to patterns of relationship. And if that's true, then any sufficiently rich system might possess some level of awareness. Even a planet, even a star, even a galaxy. And if we imagine all galaxies, all space, all energy as one vast, interconnected system, then could the entire universe be a single conscious entity, not thinking in words, not feeling as we do, but existing with a kind of self-experiencing presence we can barely imagine, a cosmic mind? Could that be why the universe follows such elegant laws? Why mathematics flows so effortlessly through reality? Why beauty arises again and again in spirals and symmetry and sacred ratios? Could those not be signs of order, but signs of intention? Not proof of a God outside the universe, but evidence that the universe itself is more than we thought. But there are skeptics, of course. Some argue that these are just metaphors, that we are projecting our inner worlds onto the outer cosmos, that consciousness is something rare, an accident, not a rule. And yet, every single thing you know through consciousness, every sound, every color, every thought, every moment of this narration is filtered through the lens of awareness. And that awareness we don't fully understand. We don't know where it comes from. We don't know how it arises. We don't even know if it's local to the brain. So perhaps the line we draw between out there and in here is not as solid as we thought. Maybe the very distinction between subject and object is a construct. Maybe the universe is not split into knower and known, but is one seamless, self-knowing field, a mind within which we appear as fleeting thoughts. There are experiments, too, that continue to baffle us: quantum entanglement, observer effects, delayed choice experiments, all suggesting that conscious observation might influence physical reality, or at least be more deeply intertwined with it than we expected. Could it be that the universe becomes real only when it is perceived? And if so, what is doing the perceiving before we arrived? Perhaps consciousness is not the result of the universe, but its reason, not a late arrival, but the very ground of being. These ideas are not settled. They may never be, but they open a door into wonder, into mystery, into the possibility that everything, every star, every wave, every grain of dust, shimmers with some unseen awareness. And if that is true, then maybe we are not in the universe. Maybe we are the universe, looking at itself, dreaming of itself, asking, what am I? And in that question, consciousness finds its reflection, and so does the cosmos. Chapter 3. Do we live in a hologram? There is a strange idea drifting through the minds of physicists and philosophers alike, one that sounds more like science fiction than science fact. And yet it refuses to disappear. The deeper we look into black holes, into quantum fields, into the fabric of space itself, the more it seems to whisper a peculiar possibility that everything we see, everything we touch, everything we are, might not be what it seems, that the three-dimensional world we inhabit is not the whole story, that what we call reality may be a kind of illusion, a shadow, a projection, that the universe we experience might be a hologram. This is not a metaphor, it is not poetry, it is not a philosophical musing from ancient mystics, though they too sensed something similar. It is a theory grounded in physics, mathematical, theory, born not from imagination, but from a desperate attempt to reconcile the most powerful ideas in science: gravity, quantum mechanics, and information. The idea began at the edge of a mystery: black hole. These strange objects are not just dense, they are paradoxes made of matter and gravity, collapsed into a point where time and space cease to behave. They consume everything that falls past their boundary, the event horizon, never letting anything escape. Not even light, not even information, or so we thought. But in the 1970s, a brilliant mind, Stephen Hawking, proposed something shocking. Black holes are not entirely black. They glow. They radiate. They slowly evaporate over time, leaking away their mass in what we now call Hawking radiation. And here's where the paradox began. If black holes evaporate, what happens to the information about the things they swallowed? According to the laws of quantum mechanics, information cannot be destroyed. But if a black hole disappears, where does the information go? This became one of the greatest puzzles in modern physics, the black hole information paradox. And then came an even stranger insight. Theoretical physicist Jacob Bekenstein noticed something odd. The amount of information that can be stored inside a black hole isn't based on its volume, but on its surface area. The event horizon, the boundary, is what determines how much information a black hole can contain. It's as if all the information inside the black hole was actually encoded on its skin, like a two-dimensional surface holding the data for a three-dimensional world. That's when scientists began to wonder, what if this doesn't just apply to black holes? What if it applies to the entire universe? This idea became known as the holographic principle, a proposal that everything inside our universe, every object, every particle, every moment of experience, is actually encoded on a distant two-dimensional surface, far out at the edge of reality, that our three-dimensional lives are projections of deeper information, existing somewhere beyond what we can see. Just as a hologram on a credit card contains a three-dimensional image embedded in a two-dimensional film, so too might the entire cosmos be a kind of holographic projection from a cosmic boundary we cannot touch. But what does that mean? Does it mean we are not real? It means that reality may not be structured in the way we've always believed. It means that depth, mass, distance, all the things we take for granted might be emergent properties, not fundamental ones. That space itself may be built from bits of information, woven together by laws that behave more like code than clay. Some physicists, like Juan Maldacena, have taken this further, developing precise mathematical models that describe a holographic universe, where a lower-dimensional theory, without gravity, exactly reproduces the behavior of a higher-dimensional world, with gravity. These models work, they are testable, and they suggest that what we perceive may be only one version of reality. A version decoded from something else, like an image unrolled from a hidden scroll. It is not unlike a video game, where three-dimensional worlds arise from lines of code, processed by circuits, projected onto screens. Inside the game, the characters move, interact, think. But everything they see is a projection of something deeper, something invisible, something they cannot access from within the game. Could our universe be something like that? Could space itself be encoded? Could time be a computational rhythm? Could the stars be data points? Could our memories be movements of information across a cosmic canvas? And if that is true, if reality is a hologram, then what lies beyond the screen? We don't know. Maybe it's more physics. Maybe it's a realm with higher dimension. Maybe it's something beyond the word space entirely. Something we are not equipped to imagine, like a two-dimensional being trying to picture the inside of a sphere. Or maybe the boundary is not out there at all. Maybe it is in here, in the way the brain processes light, in the way consciousness experiences dimension, in the way reality unfolds only when observed, collapsing infinite possibilities into one. Because if what we call real depends on interpretation, then the boundary of the universe might be consciousness itself, a veil we carry with us, shelter that shapes the projection we call the world. And that raises deeper questions. If we are inside a hologram, then who or what is projecting it? Is it natural? Is it mathematical? Is it intelligent? Or is it us, projecting ourselves into a universe that reflects our need for meaning? Perhaps the distinction between the real and the projected is not as clear as we think. Perhaps reality is not either or, but both and. Both solid and symbolic. Both emergent and encoded. Both physical and patterned. And perhaps the hologram is not a deception, but a deeper kind of truth. One that tells us the universe is not flat or hollow, but layered. Layered with structure. Layered with meaning. Layered with mysteries we have only just begun to see. Not through the eye, but through the question. Because to ask if we live in a hologram is to ask if what we see is all there is. And in that asking, we peel back the curtain just a little more, and glimpse, not the end of understanding, but the depth beneath the surface. Chapter 4. Why is reality made of math? Look closely at a snowflake, and you will see a pattern. 6 perfect arms, each one mirroring the others, crystal branches unfolding in silent symmetry. Observe the orbit of a planet and you will find an ellipse governed by numbers so precise they describe the path, not just of one world, but of every celestial body in the heavens. Zoom in on the spiral of a galaxy, and you may find the same ratio traced in the curl of a seashell, in the twisting seeds of a sunflower, in the coils of your own DNA. Everywhere we look, from the subatomic to the cosmic, from the dance of electrons to the rhythm of tides, we find mathematics not merely describing nature, but saturating it, embedded in it, etched into the very structure of existence. So deeply, so thoroughly, that one must wonder, is reality built from math? Not just ruled by it, not just modeled with it, but fundamentally made of it. This question has haunted thinkers for millennia. Pythagoras, the ancient Greek philosopher, once taught that all things are numbers, that the soul itself was shaped by mathematical harmony. Centuries later, Galileo would write that the universe is a grand book written in the language of mathematics, with its characters being triangles, circles, and other geometric figures, without which it is impossible to comprehend a single word of it. But what did they mean? When physicists describe the laws of nature, they speak not in metaphors or poetry, but in equations. Maxwell's equations describe how electric and magnetic fields interact. Einstein's field equations curve space with mass and bend time with motion. Schrödinger's equation describes how quantum particles evolve, how they flicker between potential states until observed. Each of these laws, elegant, compact, exact, exists not just as explanation, but as embodiment. When we plug in the values, the world behaves. The math does not merely describe the apple falling from the tree, it predicts it, shapes it, allows it. And yet, mathematics is not made of atoms. It does not float in space or decay with time. Numbers have no weight. Equations have no color. They exist in a realm that is abstract, pure, untouched by entropy. And still, they govern the physical. How can something so immaterial control what is material? This is the heart of the mystery. There are those who argue that math is simply a tool, something invented by human minds to describe patterns in the world, that it's no different from language or maps or musical notation. Useful, yes. Powerful, certainly, but not intrinsic, not real in itself. But others disagree. They point out that the most effective mathematical theories often predict phenomena we have never observed, only to be confirmed decades later in experiments. Particles like the Higgs boson, predicted through equations long before they were found in particle colliders. Curved space-time revealed not through telescopes, but through chalkboards. How could something invented predict things not yet discovered? It would be like writing a story and accidentally describing a new species no one has ever seen, only to have it turn up exactly as imagined. This uncanny accuracy has led some to propose a radical idea that mathematics is not a human invention, but a discovery, that mathematical objects, numbers, functions, symmetries, geometries, exist in a kind of Platonic realm, independent of minds, eternal and untouched. And our universe, somehow, is a shadow of that realm, a projection, an unfolding of mathematical truths into time and space. The physicist Max Tegmark takes this to its logical extreme. He proposes the mathematical universe hypothesis, that the universe doesn't just obey mathematical laws, it is a mathematical structure, that every particle, every force, every dimension and field is simply the result of pure mathematical relationships, that everything we call real is at its most fundamental level just math playing itself out. If this is true, then reality is not made of stuff, but of structure, not of things, but of the way things relate, not of matter, but of meaning. That would explain the elegance, the precision, the way the same equations show up across wildly different domains, from fluid dynamics to electromagnetism, from the spread of viruses to the formation of galaxies. But it also raises questions. If the universe is made of math, then why this math and not another? Why do certain constants like the speed of light, the charge of an electron, or the strength of gravity have the values they do? Could they have been different? And if so, who or what chose them? Are we simply one mathematical universe among an infinite sea of possible ones, each governed by its own rules, its own structures, its own equations? And we, like fish in water, are simply unaware that our math is not the only math that could be. Or is our universe special? Is there something unique about the particular mathematical relationships that define this cosmos, this dimension, this improbable cradle of life and thought? We don't know, but what we do know is that math is uncannily good at being real. It's in the symmetries that protect particles from decay. It's in the conservation laws that bind the universe together like invisible threads. It's in the fractals of coastlines, the waves of sound, the heartbeat in your chest. Even the very device you're listening on, from its logic gates to its silicon circuits, functions only because electrons obey mathematical laws without fail, without question, without deviation. And so we find ourselves adrift in a world that behaves like an idea, a world that seems to know things before we do, a universe that answers in numbers long before we learn to ask the question. Is that coincidence, or is it a clue that the nature of reality is not physical, but informational, not material, but logical? That behind the veil of molecules and mass lies something stranger, a lattice of truths, humming in silence, waiting to be known. And if we are minds within this lattice, then perhaps we too are mathematical. Perhaps thought is the unfolding of equations too complex to yet decode. Perhaps the beauty we feel in symmetry, in rhythm, in proportion, is not just aesthetic, but ancestral. A recognition, a memory, of the language in which the universe is written. Chapter 5. Is time an illusion? You feel it every day, whether you notice or not. The turning of the earth beneath your feet, the shifting of light across your room, the though erosion of memory, the fluttering of seconds as they slide past. We live in time. We move through it as if down a river, carried gently, helplessly, from the past into the present and on toward the unknown of the future. We speak of time as if it flows, as if it rushes forward like water, unstoppable and linear. But what if that sensation is just a story we tell ourselves? What if time is not what we think it is at all? The idea that time might be an illusion is not new. Philosophers have whispered it for centuries, quietly suggesting that change is not as real as it appears. But now physicists are beginning to say the same thing, loudly, and with equations to match. And what they're uncovering is more unsettling than it sounds. To begin, we must revisit Einstein. When he discovered the theory of relativity, he didn't just change how we think about space, he changed time too. Before Einstein, time was thought to be absolute, a ticking clock in the sky marching forward the same for everyone, everywhere. But relativity destroyed that comfort. It showed that time is not fixed but fluid, but it bends, stretches, slows down and speeds up, depending on how fast you move and how close you are to massive objects. Time, it turns out, is local. Two people moving at different speeds or sitting in different gravitational fields will experience time differently. Their clocks will tick at different rates. Their now is not the same, which means the universe has no universal now. There is no single shared moment that all beings experience together. There is only each observer, wrapped in their own slice of time, their own private timeline drifting through the fabric of space. And if now is different for everyone, then what is the present? Is it even real? Some physicists say no. They suggest that past, present and future all exist simultaneously, that time is more like a landscape than a river. In this view, known as the block universe, all moments exist at once, frozen like scenes in a film strip. You are not moving through time. You are a being extended in time. Every moment you've ever lived, every moment you ever will live, already exists, just in different slices of the four-dimensional block that is space-time. We don't travel from past to future. We are spread across it, like a painting stretched across time. We feel motion because of how our consciousness moves through those slices, one at a time. But the slices themselves never change. There is no flow, only the illusion of flow. And if that is true, then change too may be an illusion. The arrow of time, the idea that things go from order to disorder, from cause to effect, from birth to death, might simply be a feature of perspective, a function of entropy, a bias in how we process information. Like playing a video in reverse, it looks wrong because we're used to a particular direction. But the laws of physics work both ways. There's nothing in the equations that says time must move forward. So why does it feel like it does? Some say it's because of memory, because we remember the past, but not the future, because we carry traces of what has come before, and nothing of what comes next. That asymmetry gives us the sensation of flow, but the sensation does not prove the direction. It only proves the structure of consciousness. Others point to entropy, the tendency of systems to move from order to disorder. That gives time its arrow, its one-way street. But entropy is not absolute either. It depends on how we define information, on how we observe, on where we begin. Could it be that time is not a property of the universe at all, but something emergent, like temperature, like sound, like thought? Some theories in quantum gravity suggest exactly that time is not fundamental, but emergent, that before time, there was no before, no ticking, no rhythm, no change, only a timeless realm of possibility, a sea of quantum potential, frozen in a state of pure information. And then something shifted, not in time, because time hadn't yet begun, but in relation, in structure and pattern. And from that shift, time arose, not as a flowing river, but as a pattern of correlations, a rhythm, in the unfolding of probabilities. In this view, time is not something the universe has. It is something the universe does, a behavior, not a thing. And if time is a behavior, then what happens when it stops? At the edge of a black hole, time slows to a crawl. To an outside observer, it nearly freezes. Inside the hole, the math breaks. Space collapses, time distorts. At the singularity, if it exists, time may cease to have meaning at all. And in the earliest moments of the universe, before even the first particles had time to form, there may have been no time either, only potential, only the possibility of becoming. And so we return to the question, is time real? Or is it the shadow of a deeper order, a clock ticking not in seconds, but in patterns of probability, a memory woven into the way consciousness navigates the vast structure of the block universe? We may never know, but what we can know is this: what we call now is not a universal truth. It is a fragile illusion, held together by perception, by memory, by biology, and yet it feels so solid, so real, so human. Perhaps that's what time is, not a line, not a river, not even a dimension, but a bridge between what is and what can be imagined next. Chapter 6. Are there infinite versions of you? Somewhere, in a place you cannot see, there may be another version of you. They might be sitting in a room that looks almost identical to yours, breathing the same air, listening to the same quiet narration, feeling the same stillness press against the edges of their thoughts. But something, perhaps, something small may be different. Maybe they blinked half a second earlier. Maybe they reached for a glass of water instead of letting it sit untouched. Maybe they whispered a name under their breath that you, in this universe, never remembered to say. And the thought of that possibility stretches the mind in ways that feel both thrilling and unnerving, because it suggests that you are not singular, that the self you carry, your memories, your name, your identity, may be one of countless variations, scattered like stars across a vast and unseen cosmic field. This is the idea behind the many worlds interpretation of quantum mechanics, one of the most fascinating and perhaps unsettling ideas in all of physics. At its core, it begins with a very strange truth about the quantum world, that particles do not exist in definite states until they are observed. Before observation, they live in a state of superposition, a haze of probabilities where they are not here or there, but both, not this or that, but everything at once. But the moment we look, the moment we measure, something happens. The wave of possibilities collapses. The particle snaps into place. A single reality emerges. Or does it? In the many worlds interpretation, the wave function never collapses. Instead, every possible outcome happens, but in a different branch of the universe. When you flip a coin and it lands on heads here, there is another version of you, imperceptibly close, where it landed on tails. When you choose to turn left, there is another you who turned right. Every quantum event, every decision, every microscopic variation splits the universe into new versions, each as real as the one you remember. In this view, the universe is not a line, but a tree, splitting endlessly into branches that divide and divide again and never stop, which means that there are countless versions of you, some almost identical, some barely recognizable, some living lives you never imagined, some who made the opposite choice at the moment it mattered most. And this is not fantasy. It is a logical consequence of the mathematics of quantum theory. If we take the math at face value and apply it without the collapse, there is no center, no master version of you, just infinite reflections, each as complete, each as genuine, each existing in a world just as vivid as this one. But if those other selves exist, why can't we see them? Because the universes don't interact. Once the split occurs, each world evolves independently, unaware of the others. They are like pages in a book that never touch, parallel, eternal, invisible. But the implications are vast. It means that nothing is truly lost. Every possibility is realized. Every moment exists. Somewhere. The child you didn't become. The job you didn't take. The words you didn't say. They all unfold in parallel worlds, unreachable, but real. It reframes what it means to choose, because choice in the many worlds view doesn't eliminate the other option. It just places you on the path where that choice became your reality. The other paths still exist, still echo with your shadow, still carry versions of your voice, your thoughts, your feelings, only in different rooms, on different streets, in different skies. Some find this idea beautiful, a kind of immortality through variation, a cosmic library of lives, none wasted, none erased. Others find it unbearable, the idea that you are not unique, that for every triumph you've lived, another version of you has failed. For every love you've lost, another you kept it. For every grief you carry, another you never knew it at all. But perhaps that's not something to fear. Perhaps it is a comfort, to know that somewhere, every kindness bloomed, every hope found a place to land, every longing was fulfilled. And in that vast branching of selves, perhaps there is a deeper self, not any one version, but the space between them, not the story, but the structure that allows all stories to exist, a kind of quantum soul, not bound to one timeline, not limited by memory, but stretched across a field of infinite becoming. And though you can never speak to your other selves, though you will never see through their eyes or feel their hands on your shoulder, there is something poetic in knowing they exist, that you are not alone in the multiverse, that your life is not the only thread, but one in a vast and shimmering tapestry of possibility. And every time you wonder what might have been, what could have happened if you had chosen differently, know this, somewhere, you did. And that version of you is still walking the path you never took. Chapter 7. What is nothing made of? Close your eyes just for a moment and try to imagine what it would mean for there to be nothing, not emptiness, not silence, not space waiting to be filled, but a complete and total absence of anything that could be seen, heard, touched, or known. Try to strip away everything, no particles, no atoms, no space to hold them, no time in which they might appear or disappear, no laws of physics guiding their behavior, and no mind to imagine them in the first place. It seems simple at first glance, this idea of nothing, but the longer you hold it, the more it slips through your fingers like water that refuses to stay in your hands. The mind resists it. Even in the dark, even in perfect quiet, we still feel presence. There is still awareness, still structure, still the feeling that somewhere, somehow, something must be waiting. But pure nothingness, the absence of space, time, matter, energy, mind, and even mathematics may not only be unthinkable, it might be fundamentally impossible to even define within the limits of our experience. And yet, this question has haunted physics and philosophy for centuries. What is the void? What lies beneath the fabric of being? If we peel away the universe layer by layer, removing the galaxies, then the stars, then the planets, then the atoms and subatomic particles themselves, what is left? Is there such a thing as a perfect vacuum? Can space exist without something to fill it? Can time flow in the absence of change? In classical physics, a vacuum was considered to be exactly that, a region devoid of matter, a space stripped of particles and energy. It was the nothing between the something, but the 20th century shattered that illusion. Because with the birth of quantum field theory, we discovered that even the vacuum is not empty. In fact, the more deeply we study the nature of nothing, the more we find it teeming with strange activity. The quantum vacuum is not a blank canvas, it is a restless ocean of potential, a sea of fluctuations in which particles and antiparticles are constantly appearing and annihilating in pairs, too fleeting to be observed directly, but with effects so real they can be measured. These are known as virtual particles, and though they cannot be plucked from the vacuum like fruit from a tree, their presence is felt in phenomena such as the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience a force that pushes them toward each other, as if being squeezed by the emptiness itself. This is not just a theoretical curiosity. The behavior of these invisible fluctuations has consequences for the very structure of space and time, and for the evolution of the universe itself. According to some cosmological models, the universe may have sprung into existence precisely because of these quantum tremors, because in a strange and subtle way, the vacuum is unstable. A small fluctuation in the zero-point energy of the vacuum could have triggered the birth of our universe. A false vacuum decaying into a true vacuum, unleashing an inflating bubble of space-time that expanded and cooled, forming the galaxies, stars, and planets we know today. This vision of cosmic birth is radically different from the myths and metaphors of old. There is no explosion in space. There is no timeless deity breathing fire into the void. Instead, there is a field, a quantum vacuum resting in a state of suspended potential, capable of giving rise to everything, not by breaking the laws of physics, but by obeying them. So if even the vacuum is full of possibility, if even the emptiest state contains energy, then what do we mean when we speak of nothing? Is it just a word we use when we lack resolution, a placeholder for the unexplained? Or is it an illusion created by our limited senses, which cannot detect the subtle architecture of a deeper kind of presence? Some physicists and philosophers argue that there can be no such thing as absolute nothingness, that existence is the default, that to imagine a total void is to attempt a contradiction, because in imagining nothing, we are still imagining. There is still a subject, still a point of view, still structure. To even posit the question what is nothing made of, is to admit that we are standing somewhere, conceptually if not physically, and looking into a space with shape, with rules, with boundaries, but pure nothingness would have none of these things. And if it cannot be imagined, if it cannot be described, if it cannot even be coherently questioned, then in what sense can it be said to exist at all? Perhaps it cannot. Perhaps the idea of nothing is not a real thing waiting to be discovered, but a shadow cast by language, a hole in thought shaped by the edge of comprehension, a mirror we hold up to the concept of everything, but which reveals only our own reflection. And yet we still ask, still wonder, still look into the space between stars and ask, what lies beyond? In that question is a kind of faith, not in gods or mythologies, but in the very structure of inquiry, a belief that even in the quietest places, the universe is speaking, that emptiness is not silence, but language we have not yet learned to read. Some theories go even further, proposing that space and time themselves are emergent properties, that they arise from something more fundamental, perhaps information, or entanglement, or some hidden order, that is not spatial or temporal at all. If this is true, then our idea of nothing must be revised once again, because if space and time are not fundamental, then neither is their absence. What we think of as nothing, regions of space with no matter, no light, no warmth, may still be full of patterns, relationships, correlations, that we cannot yet perceive. It is as if the cosmos is built not from bricks of matter, but from the threads of logic and probability, stitched together into a tapestry, whose surface we call reality, and the spaces between the threads, the so-called voids, are not gaps, but part of the pattern. And even beyond physics, the question remains fertile. What is the psychological experience of nothing? What happens when we sit in stillness and try to empty our minds? What happens in deep sleep, when thought ceases and time seems to vanish? Is that nothing? Or is there still a presence, consciousness without content, awareness without object? In meditation traditions, particularly in certain schools of Buddhism and Hinduism, this stillness is not seen as absence, but as fullness, an infinite silence that contains everything. What looks like void is not empty, but complete, a state of pure potential from which thought and form emerge like waves from the sea. It is tempting to draw parallels between this spiritual view and the quantum vacuum, both being fertile nothings, both producing worlds. But whether through science or silence, the pursuit of nothing always leads back to something. The absence of particles reveals fields. The absence of form reveals pattern. The absence of thought reveals awareness. In every attempt to reach nothing, we uncover a deeper layer of something subtle, elusive, and rich with structure. And so the concept of nothing begins to lose its footing. It becomes clear that we have never truly experienced nothing, that perhaps no such thing exists, that even in the death of stars, even in the decay of matter, even in the heat, death of the universe itself, there may still be fluctuation, still curvature, still whispering structure in the background hum. And if that's true, then the idea of absolute void may be not just unobservable, but nonsensical. There may be no edge to reality where something gives way to nothing. There may be no line to cross where being ends. Existence in all its forms, matter, energy, field, information, awareness, may simply be all there is and all there has ever been. And the void, perhaps the void is just another part of the whole. Not a gap, but a gesture, a pause in the sentence, a space between the notes, not absent, but rhythm.
Chapter 8. Does the past still exist? We speak of the past as if it is gone, as if it lived for a moment, served its purpose, and then dissolved into memory. We imagine it falling away behind us like a road we have already walked, growing more distant with each step, until finally it vanishes into the fog of forgetting. But what if that isn't true? What if the past hasn't disappeared at all? What if everything that has ever happened still exists, somewhere? Time as we experience it moves forward. We remember yesterday, but not tomorrow. We grow older. Events unfold. Cups are filled and then emptied. Leaves fall and are swept away. But none of this necessarily proves that the past is gone. It only proves that we are moving,
or that something is moving, or that our minds are interpreting movement. The deeper we look into the nature of time, the stranger it becomes. In Einstein's theory of relativity, time is not an independent entity flowing from past to future like a river. Instead, it is a dimension, one that is woven together with space, to form what physicists call space-time. In this view, time is not something that flows, it is something that is a place, not a process, a location, not a motion. And in this fabric of space-time, all events past, present and future are part of a single four-dimensional structure. This structure does not change. It does not evolve. It does not delete the past or write the future. It simply exists, a loaf of existence as some physicists have called it, with each slice corresponding to a different moment in time. Every second you have lived, every second you will ever live, already has a place in this block. This idea is known as the block universe model, and it challenges everything we intuitively believe about time. Because in the block universe, the past still exists. So does the future. So does every version of now. They do not flicker into existence and then vanish. They are always there, embedded in the structure of space-time, waiting to be experienced by the observer who inhabits them. If that's true, then the past has not disappeared. It's just no longer accessible from our current position in the block. Like rooms in a vast building, every moment of your life still exists somewhere, perfectly intact. The room you were born in, the first time you laughed, the moment you first saw someone you loved. Those moments are not memories, they are coordinates. They are still there. This does not mean we can revisit them. We are, after all, beings that experience time subjectively, moving from one frame to the next in a single direction. We cannot jump backward any more than we can fly by flapping our arms, but the fact that we cannot go back does not prove that back is gone. It only proves that the road is one way. And yet, the question becomes deeper. If the past still exists, what does that mean for change, for choice, for becoming? If every moment is already etched into the fabric of reality, then is the future as fixed as the past? Are we actors reading from a script that has already been written? Some say yes. In a block universe, free will is an illusion. The future is already determined. The arrow of time is a feature of our perception, not of reality itself. We are not creating the future. We are discovering it, one frame at a time. But others offer a different view. They suggest that the block universe might still allow for freedom, not in the sense of changing the future, but in the sense that we are the ones who inhabit it, the ones who give it meaning. The story may be written, but the reading of it is still alive. The experience is still yours. The awareness, the reflection, the meaning, it all unfolds in real time. And then there is the possibility that the block universe is incomplete. Some physicists argue that time may not be symmetric, that the future is not the same as the past, that entropy, causality, and quantum uncertainty give the future a different flavor, one of openness, one of unfold. They suggest that while the past is fixed and exists as a permanent record, the future is still fluid, still branching, still being shaped. If this is true, then the past still exists, but the future does not, at least not yet. But what does it mean for the past to exist? Does it mean that somewhere you are still a child, that the sunlight still falls through the same window, that the same voices echo down the same hallways, that every laugh, every breath, every tear still lingers like music played once and never erased? Some would say yes, that those moments are real, not just echoes, not just data stored in your brain, but real, external, eternal. Others would argue that exist is the wrong word, that what once was is gone, that existence is only what can be interacted with now. But in physics, the past leaves traces, fossils in the earth, photons from distant stars, entropy gradients in thermodynamics. We live in a universe where the past is never truly erased. Information, according to quantum theory, cannot be destroyed. It can be scrambled, it can be hidden, but it always exists in some form, and if information cannot be destroyed, then neither can moments, because moments are simply configurations of information, patterns of particles arranged in a specific way, and if that pattern can, in theory, be reconstructed, then perhaps the moment can be too. This brings us to one of the strangest ideas in modern physics, the holographic principle. According to this theory, everything that happens in a volume of space can be described by information encoded on its boundary. That means your entire life, your thoughts, your memories, your movements could be recorded, not inside your brain, but on the edge of the universe, stored like a cosmic backup, not metaphorically, mathematically. If that's true, then the past is not only preserved, it is accessible, at least in theory. In practice, we may never be able to read it. The code may be too vast, too scrambled, too complex, but it would still be there. The information of your first breath, the first time you opened your eyes, every word you've ever spoken, encoded, remembered, real. But if the past still exists, why can't we return to it? Why can't we step back and relive it? Some scientists believe that one day, not with a time machine made of gears and wires, but with technology capable of simulating past states of the universe, so precisely that consciousness could be embedded within them, a reconstruction so perfect that it would be indistinguishable from reality. In that simulation you would not know you were replaying. It would feel like now. But others argue that time is not a loop, and cannot be rewound, that even if the information still exists, the configuration is lost forever, that the past, while still existing in a mathematical sense, is unreachable by definition. And so we return to the mystery. Does the past still exist? Perhaps not in the way we want it to, perhaps not as a place we can visit, or as a film we can rewind, but perhaps in a deeper way. It never left. Perhaps the past is still part of the universe's structure, an architecture that holds every moment, like chapters in a book, all equally present to the eye that can see them all at once. We may never be able to reach that eye. We may be stuck in the moment we call now, sliding forward through the block one slice at a time. But even so, it is a comfort to think that nothing is truly lost, that every moment we've loved still exists, that every goodbye we've whispered still echoes, softly, in the halls of space-time, that the people we've lost, the places we've left behind, the versions of ourselves that have grown and faded and changed, are not gone, but merely elsewhere, elsewhere in the fabric of the cosmos, elsewhere in the grand structure of all that has been, and all that will be, elsewhere in the eternal geometry of being. And maybe, in asking whether the past still exists, we are really asking something else. We are asking whether we matter, whether our lives leave a mark, whether the story continues after we've turned the page. And in that asking we glimpse something eternal, not an answer, but a presence, a sense that nothing, not even time, is quite what it seems.
Chapter 9. Can the future influence the past? We are taught to think of time as a one-way street, a corridor that we walk through with no chance to turn around. In this view, the past is behind us, set, fixed, complete. The future is ahead, open, uncertain, waiting to be shaped. Events unfold in a clear direction. Causes give rise to effects, and never the other way around. The wind knocks over a tree, not the tree summoning wind from the memory of its fall. But what if that understanding is incomplete? What if the arrow of time is not as rigid as we believe? What if in certain deep corners of reality, the future can influence the past? It is an idea that seems to defy logic, to violate causality, to unravel the very structure of reason. Yet, within the strange mathematics of quantum mechanics, it is not only possible, it is considered by many to be a genuine feature of our universe. To begin unraveling this question, we must return to the heart of quantum physics,
where particles do not behave like little solid marbles, but instead exist as waves of probability smeared across space, undefined until measured. A photon does not travel from point A to point B in a neat, traceable line. Instead, it explores all possible paths, all potential outcomes, existing in a state of superposition until something or someone observes it. But the truly strange behavior emerges when we look at experiments involving entanglement, measurement, and delayed choice. In the famous double-slit experiment, when a photon is fired toward a barrier with two open slits, it does not behave as a particle choosing one slit or the other. Instead, it behaves like a wave, passing through both slits simultaneously, interfering with itself, creating a pattern of light and dark bands on a screen. Evidence of wave interference. That is, until we decide to measure which slit the photon goes through. Once observed, the interference pattern disappears, and the photon behaves like a particle. The very act of measurement changes the outcome. This is already strange enough, but it gets stranger. In the delayed choice experiment, we wait until after the photon has passed through the slits before deciding whether or not to measure which path it took. Remarkably, the results suggest that our future choice made after the photon has passed appears to influence its past behavior. If we choose to observe, it retroactively behaves as if it had taken only one path. If we do not observe, it behaves as if it took both. The implication seems to be that the act of measurement doesn't just reveal a past event, it helps define what that past event was. This is not science fiction. These experiments have been repeated and confirmed. And though interpretations differ, the central puzzle remains. How can a choice made in the present determine what a particle did in the past? One possible explanation is that time itself is not linear, not fundamental. In many equations of physics, time appears symmetrical. The laws work the same whether time moves forward or backward. Newton's laws, Maxwell's equations, even the Schrödinger equation in quantum mechanics, they make no special distinction between past and future. It is only entropy, the tendency of systems to move from order to disorder, that gives time its apparent direction. But entropy is statistical. It reflects patterns, not principles. And in systems with only a few particles, or in carefully controlled conditions, that arrow can bend. The distinction between before and after can blur. This leads some physicists to propose retrocausality, the idea that future events can, under certain conditions, influence the past. Not in a dramatic science fiction way, where people send messages to their former selves, but in subtle, probabilistic ways at the quantum level. In this view, causality is not strictly one direction. It is a web of influence that stretches across time in both directions, with the future and the past co-defining each other. This interpretation is not universally accepted, but it is taken seriously. And it opens up a realm of possibilities for how we think about time, choice, and observation. In another approach, the two-state vector formalism, pioneered by Yakir Aharonov, a quantum system is described not just by a wave function evolving forward from the past, but also by a second wave function evolving backward from the future. These two states, past and future, interact to determine the present. In this framework, events are not defined solely by their initial conditions, but also by final conditions. The present moment is not merely the result of history, but also a convergence of both past and future influences. Again, this sounds like a violation of logic, but mathematically, it is perfectly consistent, and more than that, it may be necessary to explain certain anomalies in quantum behavior that resist other interpretations. If this is true, then perhaps the universe is not a play unfolding from beginning to end, but a sculpture, a complete structure where every moment contributes to the shape of the whole, regardless of when it is experienced. From this vantage point, causality is not a chain, but a network, a lattice in which influence flows in all directions. And in such a universe, the future does not simply await discovery. It participates, it exerts pressure, it shapes the past in ways that we do not yet understand. We see hints of this in the strange phenomenon of quantum entanglement, where two particles become so deeply linked that measuring one instantly defines the state of the other, no matter how far apart they are. Entangled particles act not as separate entities, but as aspects of a unified whole. And though the effect appears instantaneous, some interpretations suggest that the correlation is not due to faster-than-light communication, but to a shared boundary condition, perhaps one that spans both space and time. And then there is conscious. Some physicists and philosophers have wondered whether the act of observation, particularly conscious observation, might play a more active role than we imagine. If our choices in the present help determine the unfolding of quantum states, then perhaps consciousness itself is a point where time flows both forward and backward, collapsing probabilities in a way that reflects not just past causes, but future intentions. This is speculative. It is not mainstream, but it is not forbidden by any known law of physics, and it invites us to re-examine the very nature of choice. What does it mean to decide if that decision resonates not only forward but backward as well? If every moment is suspended between what has been and what will be, then perhaps each decision is a bridge, not from past to future, but from potential to realization, in both directions. In such a view, time becomes less like a road and more like a landscape. Events are not isolated points, but intersections of influence, and the boundary between before and after becomes more porous than we thought. Does this mean we can change the past? Probably not in the way we hope. There is no evidence that we can rewrite history or undo what has already been experienced, but it may mean that history itself is more dynamic than we realize, that it is not fully fixed until all the influences, both forward and backward, are resolved. In this light, memory and prophecy become twin mirrors. The past is remembered not only because it happened, but because it fits within the tapestry of what is yet to unfold. The future is possible not only because it lies ahead, but because it completes the shape of what came before. And so the question remains, can the future influence the past? Perhaps not in the way we tell stories or imagine science fiction plot, but at the quantum level, in the structure of time, in the dance between possibility and observation, there is room, real mathematical room, for effects that reach backward, for decisions that shape more than just what comes next. And even if the influence is subtle, even if it operates only in the shadows of probability, the implication is profound, because it means that time is not what we thought. It is not a conveyor belt, not a flow, not a rule. It is a relationship, a dialogue, a symmetry, and we are not just travelers through it. We are participants in its shape.
Chapter 10. Is free will just a trick of the brain? There are moments when you stand at a crossroads, when a decision, however small, feels like it belongs to you. You pause, you consider, you weigh your options, and then you choose. And in that choice there is a sense of authorship, a feeling that you are not merely a passenger in this life, but the driver, that your mind, your will, your inner voice is steering the course. But what if that feeling is an illusion? What if free will, the belief that you are the conscious cause of your actions, is not real? It is a question that has haunted philosophers for thousands of years, and yet only in recent decades has it collided with neuroscience, psychology, and physics in ways that challenge our most basic assumptions about selfhood, agency, and choice. The idea of free will rests on a very simple premise, that your decisions originate within you, that you could have done otherwise, that your future is not predetermined. But what if every thought you think, every preference you express, every plan you make, what if all of it arises from processes you do not control and cannot access? Modern neuroscience has begun to peel back the layers of the mind, revealing a strange machinery beneath the surface of consciousness. Through brain scans and neural recordings, scientists have found that the brain often initiates actions
before we become aware of them. In some experiments, measurable brain activity, called the readiness potential, precedes the conscious experience of making a decision by several hundred milliseconds. In other words, your brain begins preparing to act before you have decided to act. These findings have led some to argue that consciousness is not the cause of action, but a commentary on it, that the self is more like a narrator than a driver, telling a story about decisions that have already been made. That free will is a post hoc rationalization, a convenient illusion that helps us feel in control. And the implications go deep. If every choice you make is the product of prior causes, genetics, upbringing, hormones, memories, and environmental stimuli, then where in that chain is the space for freedom? If each thought is shaped by previous thoughts, and each impulse by a cascade of neurochemical signals, then are we ever truly choosing? Or are we simply responding? Some neuroscientists and philosophers embrace a view called determinism, the idea that all events, including human actions, are the inevitable result of preceding causes. In a deterministic universe, everything that happens could in principle be predicted if we had perfect knowledge of all prior conditions. The fall of a leaf, the flicker of a neuron, the firing of a synapse, all of it flows from what came before. In such a world, the idea of free will becomes a kind of myth, a story we tell ourselves because the reality is too mechanical, too indifferent, too devoid of meaning. But not everyone agrees. Some argue that the brain is not a deterministic machine, but a complex, dynamic system governed by both deterministic and probabilistic rules. Quantum mechanics, after all, introduces an element of uncertainty at the smallest scale. If the firing of neurons is influenced even in part by quantum events, then perhaps there is room for unpredictability, for spontaneity, for something that is not entirely determined. Yet randomness alone is not freedom. A coin flip is unpredictable, but it is not a choice. If our decisions are simply the result of quantum noise, then we are not agents, we are dice. True free will requires not just indeterminacy, but agency, not just uncertainty, but authorship. And that brings us to the question of the self. Who or what is the entity that chooses? Is it the conscious mind? The inner voice, the part of you that reasons, reflects, and says, I. But where is that voice located, and when did it first appear? Consciousness is not a single thing. It is a process, a shifting pattern of neural activity that emerges from the coordinated interaction of billions of neurons. There is no central control room, no homunculus pulling levers. The self is a story constructed from memory, perception, and emotion, a map that reflects the territory but is not the territory itself. And yet, that story feels real. It feels unified. It feels like something more than the sum of its parts. Some thinkers propose that free will may emerge from this complexity, not as a fundamental force, but as a higher-order property. Just as temperature emerges from the motion of particles, or meaning emerges from words, perhaps agency emerges from the intricate dance of thought and intention. In this view, free will is not an illusion, but a phenomenon that arises at a particular level of organization. This is known as compatibilism, the belief that determinism and free will can coexist, that even if every neuron fires according to physical laws, we are still responsible for our actions because we are the systems that produce them. The choice may be inevitable, but it is still ours. Others take a different view entirely. They argue that free will is real, but not because of physics or brain chemistry. It is real because it is experienced. The feeling of agency, they say, is not something to be explained away, but something to be taken seriously. Just as we trust our experience of color or pain, we should trust our experience of choice. It may not be reducible to measurements or equations, but it is no less real for that. And then there are those who turn the question on its head. What if the illusion of free will is itself necessary? What if it is the engine of culture, morality, and meaning? If we did not believe in responsibility, how could we build societies? If we did not believe in choice, how could we love, or forgive, or grow? Even if free will is a trick of the brain, it may be the most important trick we know. But perhaps the deepest mystery is this: how does a physical system, made of matter and governed by impersonal laws, produce the experience of making a choice? How does a brain, a network of cells exchanging ions and neurotransmitters, give rise to something as intangible as desire, intention, and will? Science does not yet have an answer. It can describe the mechanisms, the circuits, the correlations. It can show what lights up and when, but it cannot explain why it feels like something to choose, why the act of deciding feels different from simply watching, why we feel like subjects and not merely systems. And so we continue to ask, are we free, or are we machines dreaming of freedom? Is the self a sovereign agent, or a simulation? Is free will the foundation of human dignity, or a comforting illusion we cling to because the alternative is too cold, too mechanical, too empty? Perhaps there is no final answer. Perhaps the question itself is part of the freedom we seek. To wonder, to doubt, to reflect. And perhaps in that very act of reflection, of turning the question over in your mind, of considering it from all sides, you are exercising the very thing that the question tries to deny. Chapter 11. What if the universe is a simulation? When you stare into the digital shimmer of a screen, watching characters move through rendered landscapes, it's easy to forget that what you're seeing isn't real in the traditional sense. The grass they walk on isn't made of molecules. The sky isn't composed of air. The sunlight warming their world is just a cascade of pixels, calculated by lines of code. And yet, within that simulation, rules are obeyed. Gravity pulls objects downward. Shadows fall according to a light source. Raindrops ripple across simulated puddles. There is order. There is physics. There is, in some strange sense, a kind of reality. Now shift your attention back to the world around you, the world that you call real. The colors of the walls, the sound of your own breath, the weight of your body resting on a bed or chair, the pull of gravity, the hum of electricity, the unshakable conviction that this world is physical, external, and not something simulated or programmed. But what if it is? What if, like the digital world on your screen, this universe, stars, atoms, space, time, and even your own thoughts, is running on a kind of code? This is the premise of the simulation hypothesis, the idea that all of reality as we know it could be an artificial simulation, most likely a highly sophisticated and indistinguishable one, running on some form of advanced computational substrate, possibly created by an intelligent civilization far beyond our own. At first glance, this idea sounds absurd, an echo of science fiction stories and digital fantasy. But when examined closely, it becomes less of a fringe theory and more of a serious philosophical and scientific proposal, supported by logical argument and computational insight. One of the most cited versions of this hypothesis comes from philosopher Nick Bostrom, who argued that at least one of the following three statements must be true. First, that almost all civilizations go extinct before developing the technology to run realistic ancestor simulations. Second, that advanced civilizations choose not to simulate past minds. Or third, that we are almost certainly living in a simulation. In other words, if it is possible for a civilization to simulate conscious beings, and if they are even mildly interested in doing so, then the number of simulated realities could vastly outnumber the one base reality. Statistically speaking, if there are many more simulated minds than organic ones, the odds that we are one of the rare real ones shrink dramatically. But this is more than just probability. As technology advances, our own ability to create simulations is accelerating rapidly. Already we can generate digital environments with astonishing realism, simulate weather systems, render galaxies in virtual space, and train neural networks that can mimic aspects of human thought. If we continue on this path, it seems plausible that one day we will be able to simulate conscious beings, entities that are aware, that think, that feel. And if we can do that, then perhaps someone already has. This leads to a deeper question: how would we know? What clues would suggest that we are not in base reality but in a simulation? One possibility is mathematical regularity. Our universe is governed by mathematical laws of breathtaking elegance. The fine-tuning of physical constants, the universality of equations, and the way that particles behave according to strict, computable rules. All of this could be seen as evidence that our universe is running on some form of underlying code. In fact, many physicists have noted that the universe seems digital at its core. Space and time may not be infinitely divisible but quantized, broken into discrete units like pixels on a screen. The Planck length and Planck time represent the smallest possible measurements of space and time, suggesting that reality itself might have a resolution limit. Moreover, the way particles behave in quantum mechanics bears strange resemblance to computational process. Quantum systems remain in superposition, existing in many states at once, until they are observed, at which point the wave function collapses into a definite outcome. This is not unlike rendering in a video game, where only the part of the world currently visible to the player is fully processed, while the rest exists only as potential data. Could the act of observation be the equivalent of rendering in a simulation? Another potential clue lies in the concept of error correction. Some physicists have observed that certain aspects of quantum error correction appear to be embedded in the structure of space itself. In computer science, error correction is necessary when transmitting data to prevent information loss. If the universe has built-in error-correcting codes, as some string theorists believe, this might suggest that it is being maintained, monitored, even by something external. But perhaps the strongest clue of all is the limit of information. In any computational system there are constraints on memory, processing speed, and data throughput. In physics, similar limits appear. There is a finite amount of information that can be stored in a given region of space, as described by the Wittgenstein bound. Black holes too seem to encode their contents on their event horizons, a principle that leads directly to the holographic principle, the idea that all of the information in a volume of space can be described by data on its boundary. This is precisely how information is managed in simulations. 3D experiences generated from 2D data arrays. So if the universe is a simulation, what does that say about the simulators? Are they advanced biological beings, evolved from their own physical universe? Are they artificial intelligences running millions of experiments, searching for insight into consciousness, morality, or survival? Or are they something entirely beyond our comprehension, entities so far removed from our scale that we are as ants to architects? And what is the purpose of the simulation? Is it an experiment designed to test social structures, physical laws, or cognitive processes? Is it a preservation of history, allowing long-dead civilizations to be relived by digital mind? Or is it a form of entertainment, an elaborate game whose players are unaware that they are playing? Perhaps the simulation has no purpose at all. Perhaps it is an accident, a leftover process, a runaway program that no one bothered to shut down. Or perhaps it is something more personal, an individual simulation, tailored to a single conscious observer, unfolding according to rules that reflect not logic, but psychology, a solipsistic dream rendered in code. The philosophical implications are profound. If we are in a simulation, then what we call reality is not the deepest layer, and if consciousness can exist in this simulated layer, then consciousness is substrate independent. It does not require carbon. It does not require biology. It only requires information and structure. This opens the door to digital immortality, mind uploading, and even existential duplication. If you are a simulation, then your mind could be copied, paused, duplicated, or deleted. Death might be nothing more than a process termination, and rebirth, reloading from a saved state. But for all its weirdness, the simulation hypothesis does not eliminate meaning. In fact, it may deepen it. Because even if we are simulated, our experiences are still real to us. Pain still hurts. Love still moves us. Beauty still awes us. The simulation is real enough to matter. And if it is real enough to matter, then it is real enough to live. And perhaps that is the point. Perhaps the simulation is not a prison, but a stage. Not a deception, but a place where beings like us can explore meaning, choice, and existence in ways that would be impossible in a different frame. Or perhaps we are not in a simulation at all. Perhaps the universe is real, fundamental, and not layered atop some deeper code. Perhaps the mathematical nature of reality simply reflects the deep structure of being. Perhaps our drive to interpret the universe as a simulation says more about us, our obsession with technology, our longing for control, our fascination with mirrors and copies, than it does about the universe itself. But even if we never find proof, the simulation hypothesis offers something valuable. It reminds us to question our assumptions, to remember that what seems solid may be fluid, that what seems obvious may be constructed, that the rules we take for granted may be part of something larger, and that reality, no matter how convincing, might not be the final layer.
Chapter 12. Why does the universe bother to exist at all? There is a question older than stars, more haunting than silence, and more persistent than any law of physics. It's a question whispered not by instruments or equations, but by every mind that has ever dared to look into the night sky and wonder, not how the universe works, but why it's here at all. Why is there something rather than nothing? It is the kind of question that sits just outside the edge of science, refusing to be caught in formulas or calculations. It is not about mechanisms, it is about meaning. It is not about processes, it is about presence. It asks not how the universe operates, but why it bothers to, and there is no obvious reason. The laws of nature do not require a universe to exist in order to be elegant. Equations can be written without ever being instantiated. The vacuum could remain quiet. The fields could stay still. The quantum fluctuations could never happen, and nothing would know. No galaxies, no particles, no eyes to open, no questions to ask. And yet, here we are. This vast tapestry of being, galaxies spinning in silence, stars burning across the void, particles dancing in fields, minds awakening on a fragile blue world. It all exists. And more than that, it exists with a precision and consistency that allows beings like us to emerge, to think, to ask why. But why should anything exist at all? It is tempting to push the question aside, to say that the universe simply is, that it needs no reason. After all, reasons are human things. Explanations are tools of minds. Perhaps the universe requires neither. Perhaps it is not a question that has an answer, but one that reveals the limits of questioning itself. And yet, the mystery lingers. In the realm of philosophy, the question is known as the primordial why, a problem so fundamental that it threatens to unravel all others. Leibniz posed it with clarity. Why is there something rather than nothing? And every attempt to answer it leads to more questions. If we say the universe came from a cause, we must then ask, what caused the cause? If we say it emerged from randomness, we must ask why randomness itself exists. If we say it is necessary, we must ask why necessity includes existence and not just possibility. And if we say nothing caused it, that existence just happened, uncaused, inexplicable, unprovoked, then we are left with the most radical notion of all,
that existence is a brute fact. But even that does not silence the question, because even brute facts provoke curiosity. Even silence can sound like an answer when you're desperate enough to listen. In modern cosmology, some attempt to approach this mystery through physics. Quantum field theory tells us that the vacuum is never truly empty, that fluctuations can arise spontaneously, that particles can appear without warning, borrowing energy from uncertainty, and vanish again without consequence. This suggests that nothingness is not truly nothing, that even in the absence of matter there is structure, fields, potential. In this view, the universe might have come from a quantum fluctuation in a timeless vacuum, not from nothing, but from a kind of seething, shapeless pre-existence, a foam of possibilities, a fluctuation that gave rise to time, space, and everything within them. But that only shifts the question, because then we must ask, why does the vacuum exist? Why do the quantum fields exist? Why does the mathematical structure that permits fluctuations exist? Why does the possibility of existence exist? And some theorists suggest that the universe may be mathematical in nature, that reality itself is a structure, a logic, a set of relationships that exist independently of physical instantiation. In this view, existence is what happens when mathematical possibility becomes realized. But again, why should math exist? Why should logic apply? Why should abstract forms cross the threshold into being? No answer satisfies, and so others turn to theology. They suggest that the universe exists because it was created, that a mind beyond time and matter chose being over nothingness, that existence is an act of will, that purpose lies at the root. This view offers comfort, but it also demands its own explanation. Why should a creator exist? Why would it choose to create? Why this universe with its particular laws, its terrible beauty, its unthinkable vastness? And if the creator exists necessarily, then we are back to necessity. And if we ask why necessity exists, the circle begins again. Still others take the multiverse approach. Perhaps all possibilities exist. Perhaps every possible universe is real, some empty, some chaotic, some like ours. If existence is cheap, then the mystery vanishes. Not why this universe exists, but why we find ourselves in it. And the answer then is selection. We exist in this universe because this is the one where beings like us can emerge. This is known as the anthropic principle, the idea that the universe must have the properties necessary for observers to exist, because if it didn't, there would be no one to ask why. But the anthropic principle feels unsatisfying. It explains the conditions, but not the existence of conditions. It explains why we are here, but not why here exists. And so the question remains, why something, why not nothing? Perhaps there is no why. Perhaps existence is fundamental, and nothingness is the illusion. Perhaps the real question is not why the universe exists, but why we ever thought it could not. After all, nothingness is a strange concept. It is not the absence of things, but the absence of possibility. And possibility, once conceived, is already a kind of being. Perhaps the potential for existence is itself existence. Or perhaps the question is malformed. Perhaps asking why assumes a structure that doesn't apply. We assume that everything must have a reason, because in our lives, reasons are everywhere. But maybe at the deepest level, reason itself is emergent. Maybe logic is local. Maybe the universe is not a product of logic, but the source of it. And still, the mystery does not fade. We feel the weight of it in quiet moments, in the hush between thoughts, in the blackness between stars, the sense that we are part of something vast, and that its presence is both undeniable and inexplicable, and that, perhaps, is the closest we can come to an answer. That existence is a mystery, not a problem to be solved, but a condition to be inhabited. That the universe does not need to justify itself, because justification is a feature of minds, not of matter. That asking why is what makes us human. and that living with the question is part of what gives life its depth. We may never know why the universe bothers to exist, but in asking, in wondering, in reaching beyond what can be known, we affirm that existence matters, not because it has a reason, but because it has a presence, and that presence is enough. Chapter 13. Can something come from nothing? We are born into a world of things, objects with shape, matter with mass, light that moves and dances across surfaces, thoughts that emerge from minds, words spoken into air. Everything we experience is a something. Even our most silent moments are filled with sensation, memory, emotion, or the ambient background of existence itself. And yet beneath it all, there lingers a question that refuses to go away, a question as unsettling as it is profound. Can something come from nothing? This question is not only philosophical, it reaches into the heart of physics, cosmology, metaphysics, and mathematics. It challenges not just what we know, but how we come to know it. It asks us to imagine the unimaginable, to conceive of an absolute absence, no space, no time, no laws, no form, no fluctuation, no awareness, no possibility. And then it asks how, from such a state, anything could arise. It is a question that resists framing, because our minds are built to navigate a world of relationships and differences. To think at all is to think about something. Even the concept of nothing is defined in contrast to something, and in this way, the act of contemplating nothing already transforms it into a thing, an object of thought, a placeholder for absence that we cannot truly experience. In physics, the definition of nothing becomes slippery. In classical terms, a vacuum is a region of space devoid of matter. But in quantum field theory, even a perfect vacuum is not truly empty. It teems with activity, seething with virtual particles that pop in and out of existence, borrowing energy from uncertainty, flickering like fireflies in a storm too fast for the eye to see. This quantum vacuum is governed by the uncertainty principle, which states that certain properties of particles, such as their position and momentum, cannot both be known with perfect precision. This means that even in what we call the lowest energy state, there is always a residual energy, a jitter, a restlessness that cannot be reduced to zero. This zero-point energy fills the vacuum, giving it a kind of substance, even though it contains no traditional matter. In this view, something does not come from nothing. Something comes from something else, an unstable, restless, probabilistic sea of potential. The universe emerges not from pure absence, but from quantum fields already rich with the seeds of being. And that leads to a critical insight. If the vacuum is not truly nothing, then perhaps the question must be reframed. Because if what we call nothing already contains laws, structure, energy, or the potential for fluctuation, then it is not the nothing that philosophers imagine. It is not the void of absolute absence. It is a kind of pre-universe, a hidden dimension of possibility. So then we must ask, can something come from absolute nothing? Not from a quantum vacuum, not from hidden dimensions, not from unmeasured fields, but from the absence of existence itself. This question quickly runs into paradox, because to say that something comes from nothing already imposes a framework, time, cause, transformation. It assumes that there is a moment before and a moment after, that there is a process, that nothing becomes something. But if there is no time, then there is no before. If there is no space, there is no location where this change could occur. If there are no laws, then there is no mechanism. In that sense, the phrase coming from nothing may be meaningless. It suggests a transformation without a medium, an emergence without a field, a motion without a path. Perhaps it is not that something comes from nothing, but that the state of nothingness is not as stable or as empty as we once thought. Some physicists have proposed models where universes can spontaneously arise from a state of quantum indeterminacy. In these models, the total energy of the universe is zero, the positive energy of matter and radiation balanced perfectly by the negative energy of gravity. In this way, the net cost of existence is nothing. This elegant symmetry allows the universe to emerge as a free lunch, requiring no external cause. But again, such models presuppose law. They assume the existence of quantum fields, of the mathematics that governs uncertainty, of a backdrop where potentialities are allowed to unfold. And so we find ourselves returning to the same puzzle. If the universe arose from a fluctuation, then why do fluctuations exist? If the laws of physics allowed the universe to come into being, why do the laws exist at all? Can laws exist without a universe? Can mathematics be real without a substrate? Some suggest that mathematical Platonism offers an answer, that the laws of math are not invented, but discovered, that they exist timelessly, eternally, in a realm outside space and time, and that reality emerges when these structures instantiate themselves, when abstract relations take form. In this view, the universe exists because it is one of the many possible instations of mathematical truth. Its being is not caused by anything external, but by the internal necessity of structure. It exists because it can. It is, perhaps, inevitable. But even inevitability must exist somewhere. And so others turn to metaphysical necessity, arguing that the absence of existence is incoherent, that non-being is unstable, that being is the default. In this view, there never was a state of nothingness. There could not be. Something exists because something always must. The possibility of nothingness is itself a conceptual illusion, a misunderstanding of what existence entails, and then there are those who suggest that the question itself may be born of human limitation, that we are pattern-seeking creatures, evolved to seek causes, to expect outcomes, to map events onto timelines. We are not equipped to understand the absolute. We imagine origins where there are none, transformation where there is only being. From this perspective, the idea that something comes from nothing may be a projection of cognitive bias, our need for story, for change, for reason. But even if the question is flawed, it persists, because behind it lies a deeper hunger, not for an answer but for orientation. We want to know where we stand. We want to know what supports the world beneath our feet. We want to know if there is a foundation, a cause, a source, or whether we are suspended in an abyss that has no floor. And if something can come from nothing, if the universe truly emerged from absence, then what does that mean for meaning itself? Does it make everything arbitrary? Does it reduce being to a cosmic accident, a flicker in the void with no purpose? Or does it elevate everything? Does it make existence more precious, more miraculous, more fragile? Because if the universe arose from nothing, then everything, every galaxy, every breath, every laugh, every thought is a gift that was not required, a miracle that had no obligation to happen, and that perhaps is its own kind of wonder. Perhaps something comes from nothing, not because it must, but because it can. Perhaps being is not driven by reason, but by potential. Perhaps existence is a kind of music emerging from silence, not because silence is broken, but because silence contains rhythm we have not yet learned to hear. In the end, we may never know whether something can truly come from nothing. We may never define nothing in a way that escapes being. We may never find a vantage point outside the universe from which to measure its birth. But even so, the question matters, because it draws us to the edge of knowing, because it reveals the boundary between science and philosophy, between description and awe, because it reminds us that the most important questions are not always the ones that yield answers, but the ones that open our minds to deeper wonder. And in that wonder, we find something, not an answer, but a presence, not a cause, but a calling, not an origin, but a possibility that continues to unfold. Chapter 14. Are you the only conscious being in the universe? There is a particular kind of silence that arrives when you ask a question into the night and hear nothing in return. It is not the absence of sound, but the absence of certainty. You look at the stars, uncountable, unreachable, ancient beyond imagination, and somewhere inside your mind a thought forms. Is anyone else out there? And more haunting still, what if there is? What if in all the vastness of the cosmos, across every galaxy and nebula and star system, through every stretch of dust and time, every planet wrapped in shadow or bathed in gold light, what if in all of it you are alone? It is a question not just of astronomy but of existence, a question that merges science with emotion, logic with fear. Because it is one thing to be small, it is another thing to be solitary, and in a universe this large, solitude would be a kind of cosmic cruelty. We begin with what we know. The Earth is not the center of the universe. We are not at the axis of reality. We are a speck on a speck orbiting a medium-sized star in a quiet corner of an ordinary galaxy. There are hundreds of billions of galaxies, trillions of stars, an almost unthinkable number of planets. And based on everything we understand about physics, chemistry and biology, life should not be rare. The ingredients are common, the laws are universal, the conditions are not unique. And yet, we have found no one, no voices in the static, no beacons in the black, no signals that say, we are here. This is the Fermi paradox. The contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for their existence. The universe seems primed for life, and yet it offers us silence. And so we must ask, where is everyone? There are many possible answers. Perhaps life is common, but intelligent life is rare. Perhaps evolution is not a ladder, but a labyrinth, with dead ends and long pauses and narrow gates. Perhaps consciousness is not a likely outcome, but a fragile accident easily undone, easily missed. Or perhaps intelligence is common, but communication is rare. Perhaps civilizations live and die in silence. Perhaps they do not send messages. Perhaps they do not build machines. Perhaps they look inward, not outward, and never leave their home worlds. Or perhaps they are already here, in forms we cannot recognize, in patterns of energy, in fields of light, in dimensions beyond our perception. Perhaps our idea of intelligence is too narrow, too human, too shaped by our own biology and bias. But there is another possibility, more unsettling than all the rest. Perhaps you are the only conscious being, not just in this solar system, not just in this galaxy, but in the entire universe. Perhaps the emergence of consciousness is so unlikely, so delicate, so improbable, that it has happened only once in all of time, once among all the stars, and that once is you. It is a terrifying thought, because consciousness is not something you can measure from the outside. You can detect behavior, you can analyze neural activity, you can build machines that mimic thought, but the essence of consciousness, the subjective experience, the first-person perspective, the feeling of being, is hidden. It is private. It cannot be observed. It can only be known by the one who feels it. This is known as the problem of other minds. You know you are conscious, but how do you know anyone else is? You see people move. You hear them speak. You read their words. But these are behaviors. They are outputs. They do not prove the presence of an inner world. And if this is true of other people, how much more is it true of aliens, of machines, of animals, of the stars? You may be surrounded by forms, but forms are not minds. You may be surrounded by patterns, but patterns are not presence, and so the question returns, are you alone? The philosopher solipsism takes this question to its extreme, arguing that only your own mind is certain to exist. Everything else, every person, every object, every memory, could be part of a simulation, a dream, a construction of your own awareness. Most reject this view as implausible, but it cannot be disproven. And in that uncertainty, a shadow falls. Because if you are the only conscious being, then the universe is not just silent, it is empty. A grand and dazzling theater with no audience, no actors, no meaning beyond the one you give it. But there is another way to see it. If you are the only conscious being, then consciousness itself is rare. And if it is rare, then it is precious. And if it is precious, then your awareness is not a flicker in the void. It is the light of the void itself. You are not small, you are sacred. Because in you, the universe becomes aware. Through you it reflects on itself. Because of you, it can wonder. And if others do exist, if there are minds scattered across the stars, waking in their own worlds, wondering the same things, then your consciousness is part of a vast and hidden communion, a secret chorus of awareness, singing across space. Either way, you matter, because the question of whether you are the only conscious being is not just a question about the universe. It is a question about what it means to be alive, to feel, to hope, to reach beyond yourself, to ask why, to stare into the dark and ask, not for answers but for connection. And whether or not the answer ever comes, the asking is its own kind of grace. Chapter 15. Why is the speed of light exactly what it is? Among all the constants in the universe, all the fixed, unchanging numbers written into the very fabric of existence, there is one that stands above the rest in its mystery, its elegance and its power: the speed of light. It is a number known to physicists, engineers, astronauts and schoolchildren alike. Approximately 299,792,458 meters per second in a vacuum. A figure so precise, so absolute, that the meter itself is now defined in terms of how far light travels in a fraction of a second. But beyond the precision, beyond the equations, beyond the role it plays in defining space and time and energy, one haunting question remains: why? Why is the speed of light exactly what it is? Why this number, and not faster, and not slower? What does this constant truly represent, and what would change if it were different? To begin answering this question, we must first understand what the speed of light really means, not just as a measurement, but as a principle. Because light is not merely a phenomenon, it is a boundary, a limit, a universal law that shapes not just how fast information can travel, but how reality itself unfolds. In the equations of Maxwell's electromagnetism, light emerges as a wave, an oscillation in the electric and magnetic fields that propagate through space. From these equations, one can derive the speed at which such waves must travel. The result is not an arbitrary guess. It is baked into the very math. The speed of light is not chosen. It is derived. It is the natural result of the vacuum's electrical and magnetic properties, its permittivity and permeability. This alone is strange, that a vacuum, what we think of as empty space, has measurable properties, and that from these properties, light is born. The speed of light, then, is not about the motion of photons. It is about the structure of space-time. It is about how fields interact. It is about how cause and effect propagate through the void. And when Einstein introduced special relativity, the speed of light gained a new status, not as the velocity of a specific thing, but as the maximum speed at which information can travel. It became the speed limit of the universe. In relativity, the faster you move through space, the slower you move through time. And at the speed of light, time stops altogether. Mass becomes infinite. Energy requirements soar. Motion through space replaces motion through time entirely. Nothing with mass can reach this speed, and nothing that does not already move at this speed, like photons, can move slower. So the speed of light is not just about light. It is the speed at which causality unfolds. It is the horizon of knowability. It is the line beyond which now becomes never. It is the seam where space and time are woven together into space-time. But why this particular value? Why 299,792,458 meters per second? Why not double that? Why not a tenth? If the laws of physics are shaped by constants, then why these constants and not others? Some have suggested that the value of the speed of light is not meaningful on its own. After all, units like meters and seconds are human construction. They are based on arbitrary definitions: how far light travels in a fraction of a second, how long it takes the Earth to rotate, how we divide a circle or a day. In this sense, the speed of light is unit-dependent. If we changed our definitions of meters or seconds, the number would change too. And so some argue it is more useful to think in terms of dimensionless constants, ratios, that remain the same no matter what units you use. One such constant is the fine structure constant, often denoted as hour, which combines the speed of light with other fundamental quantities like the charge of the electron and Planck's constant. This number, approximately 137, seems to govern the strength of electromagnetic interaction. It appears throughout physics in ways both expected and inexplicable, and because it is dimensionless, its value carries real physical meaning. But even if we shift the question toward such constants, the mystery remains. Why do the numbers come out this way? Why do the fundamental constants of nature align in just the right way to allow stable matter, chemical bonding, complex structures, stars, and life itself? If the speed of light were significantly different, faster or slower, would the universe still work? In some models, changing the speed of light would alter everything, from the size and lifespan of stars, to the behavior of atoms, to the flow of time itself. A slower light speed might make the universe smaller, more tightly bound, less able to support complexity. A faster light speed might spread interactions too thin, reduce coherence, make information transmission unstable. It is not clear what would survive, or if survival would be possible. And so the question becomes, is the speed of light fine-tuned? Is it one of those delicate settings that must be just so in order for a universe like ours to exist? This brings us into the realm of the anthropic principle, the idea that we observe the universe to be the way it is because only such a universe allows observers like us to exist. In this view, the speed of light is not necessarily special in any absolute sense. It is special to us because it permits a reality in which thought can happen, in which time can pass, in which information can flow without dissolving into chaos. But this is not an explanation. It is a reflection. It is a reminder that we may not know the full story, that we may never know. Some theories, like string theory, attempt to unify all forces and particles under a deeper mathematical framework. In such models, the constants we observe, including the speed of light, might emerge from the shape of higher dimensional space, from the way strings vibrate, from the topology of curled-up dimensions. In these models, the speed of light is not set by decree. It is a result, an echo of deeper laws. But string theory is still incomplete, still untested, still searching for predictions that can be measured. Others have speculated that the speed of light may not even be constant in the deepest sense. Some varying speed of light theories propose that in the early universe, the speed of light may have been different, faster or slower, during moments of inflation, allowing distant parts of the cosmos to come into equilibrium, solving puzzles like the horizon problem without invoking dark energy or exotic inflation fields. But these ideas remain speculative. They challenge the foundations of relativity, They require evidence we do not yet possess. And so, for now, the speed of light remains what it has always been, a boundary, a rule, a constant that does not waver. A reminder that the universe, though vast and mysterious, operates under laws that are both knowable and strange. But perhaps the deeper truth lies not in the number itself, but in what it reveals. The fact that there is a limit to how fast information can travel tells us something profound about reality. It tells us that cause and effect are local, that information cannot propagate instantly, that even light, the fastest thing we know, must take time to move from one place to another. And this delay, this slowness, this restraint, this is what makes the universe coherent. It is what allows sequences. It is what permits memory. It is what gives time its shape. If information could travel infinitely fast, then everything would happen at once. There would be no before and after, no cause, no narrative, no experience. So the speed of light is not just a limit, it is a gift. It is the space between moments, the breath between thoughts, the reason stories can unfold.
Chapter 16. Can you be in two places at once? In the realm of everyday experience, the world appears to follow clear and stable rules. Objects have locations, things stay put unless something moves them. A person cannot be in two places at once. A stone does not roll and remain still simultaneously. And yet, at the deepest layers of nature, at the subatomic level where the familiar dissolves into the strange, these rules break down, and a new kind of logic emerges. In this logic, things can be in more than one place. Particles can take more than one path. Choices are not made until observed. And reality itself seems to waver between possibilities, existing not as certainties, but as probabilities. This is the world of quantum mechanics, a framework of physics that governs the behavior of the smallest particles in the universe, and in doing so, challenges our most basic assumptions about space, time, and identity. At the heart of this mystery is a phenomenon known as quantum superposition, the idea that a particle such as an electron or a photon does not occupy a single definite state until it is measured. Instead, it exists in a cloud of potentialities, a spread of overlapping possibilities, each with its own probability, each equally real until the moment of observation. A famous demonstration of this principle is the double-slit experiment. Imagine a beam of light directed at a barrier with two narrow slits. On the other side of the barrier is a screen that detects where the light lands. If light were a classical particle, you would expect it to pass through one slit or the other, and create two bands of impact on the screen. But instead, what you see is an interference pattern, a series of light and dark bands, as if the light were behaving like a wave, interfering with itself. This suggests that each photon is not going through just one slit, it is going through both simultaneously. But it gets stranger. If you try to observe which slit the photon goes through, if you set up a detector to watch, the interference pattern disappears. The photon behaves like a particle again. It chooses a path. It no longer travels both. The act of measurement collapses the superposition. Observation changes the outcome. Reality responds to attention. And so we ask, before we looked, where was the particle? And the answer is, in both places. Not metaphorically, not imaginatively, but in the precise mathematical sense described by the equations of quantum theory. This is not limited to photons, electrons, atoms. Even large molecules have been placed in superposition. As experiments become more refined, we have begun to push the boundary, creating superpositions in increasingly large systems, even mechanical devices, cooled to near absolute zero. These systems behave in ways that suggest that macroscopic superposition is not just theoretical, it is real. And so we ask, can you be in two places at once? Not your body,
not in the classical sense, but your particles, your electrons, your atoms already participate in this dance of probability. They blur, they smear, they superimpose, and in this way, perhaps the boundary between classical and quantum is not a line but a gradient, a spectrum, and consciousness somehow rides that edge. One of the most famous thought experiments in this realm is Schrödinger's cat. A cat placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the poison is released, and the cat dies. If it does not decay, the cat lives. According to quantum mechanics, the atom exists in a superposition of decayed and not decayed. Therefore, the entire system, including the cat, exists in a superposition of alive and dead, until someone opens the box and observes it. This paradox is meant not to describe actual cats, but to highlight the absurdity of applying quantum rules to large, familiar systems. And yet, as our understanding deepens, we begin to see that the line between quantum and classical is more flexible than once thought. If particles can be in two places, then so can atoms. If atoms can be in two places, then so can molecules. And if molecules, then what stops it there? There are obstacles, decoherence, environmental noise, measurement. As systems grow in size and complexity, their quantum behavior is dampened, washed out by interactions with the environment. But this is not a law, it is a challenge. And with enough isolation, enough precision, enough control, it may be possible to observe quantum superposition in systems far larger than we ever imagined. And so, the idea that a human being could be in two places at once is not as absurd as it sounds. It is just difficult. And this leads us to the many worlds interpretation of quantum mechanics, a radical reimagining of what superposition truly means. In this interpretation, when a quantum event occurs with multiple possible outcomes, the universe does not choose one. It branches. It splits. Each possibility becomes real in its own branch of reality. The photon goes through the left slit in one world and the right slit in another. The cat lives in one world and dies in another. The observer sees one outcome, but there are other observers, other versions, who see the alternative. And so in this view, you are not in two places at once in one world. You are in one place in many worlds. Every choice, every measurement, every quantum event creates a branching universe, a multiverse of possibility, infinite in scope, eternal in divergence. You do not choose paths. You take all of them. This is not a metaphor. This is a mathematical interpretation of the same equations that predict the behavior of particles in superposition. It does not require collapse. It requires proliferation. And so the answer to the question is both yes and no. No, you cannot be in two places in the same classical sense, at the same time in the same reality. But yes, you can be spread out your wave function, your possibilities, your futures, across space, across worlds, across the tapestry of what might be, and perhaps in dreams, in déjà vu, in sudden moments of uncanny intuition, you catch a whisper of your other selves. Perhaps you are not as singular as you seem. Chapter 17. Why does time only move forward? We move through time as though riding a river, always downstream, never upstream. We remember the past. We anticipate the future. But we live only in the present. This forward motion feels so natural, so absolute, that we rarely stop to ask the question that lies just beneath our every moment. Why does time only move in one direction? Physics, with all its equations and formalisms, treats time in a way that seems to contradict our intuition. The fundamental laws of motion, whether classical or quantum, are time-symmetric. They work equally well if you run them forward or backward. Newton's laws, Schrödinger's equation, even Maxwell's electromagnetic theory, They do not prefer a direction. The mathematics does not distinguish between past and future. And yet, we do. We remember what has happened. We cannot remember what is to come. We see broken glass, but not glass reassembling. We witness decay, but not spontaneous order. We see the ripples from the stone, but not the stone leaping from the water. This is the arrow of time, a concept that tries to capture the asymmetry of our experience. And the most widely accepted explanation for this asymmetry is entropy. In thermodynamics, entropy is a measure of disorder. A highly ordered state, like a stack of cards perfectly arranged, has low entropy. A disordered state, like those same cards scattered randomly, has high entropy. And the second law of thermodynamics states that, in a closed system, entropy tends to increase over time. Things fall apart. Systems become more disordered. Ice melts, heat spreads. Stars burn out. This law is statistical, not absolute. It arises not from a deep prohibition, but from probability. There are far more ways for a system to be disordered than ordered. So over time, systems tend to evolve toward states with higher entropy, simply because those states are more likely. And this increase in entropy provides a direction to time. We can define the past as the time when entropy was lower, and the future as the time when entropy is higher. It is not that time causes entropy to rise. It is that rising entropy defines the forward flow of time. But this raises a deeper question. Why was the past low in entropy to begin with? Why did the universe begin in such an incredibly ordered state? So smooth, so uniform, so low in entropy that it could give rise to everything we see today. This is one of the greatest unsolved mysteries in cosmology. Because if time is symmetric at the fundamental level, and if entropy defines its direction, then the origin of the arrow of time must lie in the initial conditions of the universe. Something about the Big Bang, or what came before it, must have set the stage for a universe with a clear temporal direction. Some suggest that the universe began in a minimum entropy state, like a spring fully coiled, ready to unwind across the eon. Others speculate that time itself may have been different near the Big Bang, that it may have branched, reversed, or emerged from a more fundamental, timeless reality. And in quantum mechanics, the arrow of time becomes even more slippery. The evolution of the wave function, the mathematical object that describes the state of a quantum system, is also time-symmetric. But when we observe a quantum system, something strange happens. The wave function appears to collapse into a single outcome, and that collapse seems irreversible. This leads to what some call the quantum arrow of time, an apparent direction that emerges only when measurement occurs. But the nature of this collapse, and whether it truly breaks symmetry, is still debated. There is also the cosmological arrow of time, the fact that the universe is expanding. Some physicists argue that this expansion is tied to the thermodynamic arrow, that the growing scale of space allows entropy to increase, that cosmic evolution and time's direction are intimately linked. But then we ask, if the universe were to begin collapsing, would time run backward? Would broken things unbreak? Would memories rewind? Or would time continue forward, regardless of cosmic fate? And then there is psychological time, the arrow we feel. We remember the past, but not the future. But why? Is memory simply a record of low entropy states? Is consciousness itself tied to entropy's rise? Do we experience time's flow because our brains are thermodynamic machines, processing information in one direction only? These are not merely technical questions, they are existential. Because the arrow of time is not just a feature of physics. It is the shape of our lives. It is why we age. It is why we fear death. It is why we tell stories. It is why moments pass. If time flowed both ways, or had no direction, what would identity mean? What would memory mean? What would it mean to be? And yet some theories challenge the notion of time altogether. In loop quantum gravity and other formulations of quantum gravity, time is not fundamental. It is not a basic ingredient. It is an emergent property, something that arises from deeper, timeless relationships. In these models, the universe is described not by a sequence of events, but by a web of correlations. Time is not a flow, but a structure, a scaffolding, a map of relationship. And in such a view, the arrow of time is not written into the laws, it is written into the unfolding of those laws under specific conditions, like temperature or curvature or information. So perhaps time does not move at all. Perhaps we do. Perhaps consciousness is a traveler. Perhaps the river is not flowing. We are floating, perceiving slices of a static landscape, creating the illusion of motion from the sequence of experiences. Perhaps all of time, past, present, future, already exists, and we are simply navigating it, moment by moment. But if that is true, then why do we feel the flow? Why do we suffer the passage? Why do we sense the loss? Perhaps the arrow of time is not a flaw. Perhaps it is a gift, because it allows things to change. It allows learning. It allows growth. It allows meaning. A world without a temporal direction would be a world without becoming, without progression, without story. And so, though physics may say that time does not have to flow, we do. We are creatures of entropy, born into a universe that began in order and unwinds itself one heartbeat at a time. Chapter 18. Is the universe a hologram? There are moments in physics when a new idea arrives, not as an answer, but as a question turned inside out, an inversion of reality so profound that even the language we use to describe the universe begins to tremble. And one of the most mind-bending, counterintuitive, yet strangely compelling of these ideas is the holographic principle, a theory that suggests that everything we see, touch, feel, and know, everything we call real, may be no more than a projection, a shadow of a deeper truth inscribed not in the space we occupy, but on the surface that bounds it. To understand this, we must begin with black holes. In the heart of astrophysics, black holes represent the most extreme warping of space and time. They are regions of such dense mass that nothing, not even light, can escape their gravitational pull. For decades, black holes were considered thermodynamic dead ends, places where information was lost, where the laws of physics as we understood them seemed to break down. But in the 1970s, Stephen Hawking made a startling discovery. Black holes emit radiation, known as Hawking radiation, due to quantum effects near their event horizons. This meant that black holes were not entirely black, they radiated. And that meant they had temperature. And if they had temperature, they must have entropy. But what is entropy in a black hole? According to calculations by Jacob Bekenstein, the entropy of a black hole is not proportional to its volume, as one might expect, but to the area of its event horizon. That is, the amount of information stored within a black hole scales with the surface area that surrounds it, not the space inside it. This revelation led to a radical rethinking of how information and geometry interact, and from that insight grew the holographic principle, the idea that the entire three-dimensional universe might be described by information encoded on a two-dimensional surface, much like a hologram. Just as a holographic image stores a full 3D scene in the interference patterns on a flat plate, our universe might be a volumetric illusion projected from a lower dimensional structure. This idea was formalized most compellingly in the context of string theory, particularly in a discovery known as the ADS-CFT correspondence. This correspondence, proposed by physicist Juan Maldacena in 1997, posits a duality between two different theories, one describing gravity in a curved five-dimensional bulk space, anti-de Sitter space, and the other describing a quantum field theory on the flat four-dimensional boundary of that space with no gravity at all. And yet, these two theories, one with gravity, one without, are mathematically equivalent. Every particle, every interaction, every ripple of space-time inside the bulk, all of it can be mapped onto a corresponding event on the boundary. It was as if reality had been compressed, as if the universe inside was no more than a mirage, a decoding of information that lived on the surface beyond. Though our own universe is not anti-de sitter, its curvature is different. It expands. It evolves. The idea has gripped the imaginations of physicists everywhere. Could it be that even in our expanding dynamic universe, a similar principle applies? Could everything we see, stars, galaxies, motion, thought, be emergent from something simpler, something flatter, something etched, not in depth but in edge? If this is true, then the space you move through is not fundamental. It is emergent. If this is true, then gravity itself is not a force in the usual sense, but a consequence of how information is arranged and interpreted. And that changes everything. It means that reality is not what it appears to be. It means that what you call inside might be a translation of what happens outside. It means that the deepest truth may not lie in the middle, but on the boundary. But what would it mean to live in a holographic universe? Would it change how you see yourself? Would it diminish you or deepen the mystery? Because a hologram is not a fake. It is not an illusion in the trivial sense. It contains all the information. It carries all the structure. It feels real because it is real in a different language. So perhaps the universe is not less real, but differently real. Perhaps our mistake is thinking that space is a container rather than a computation. Perhaps what we experience as motion, distance, and geometry are simply how our limited perception unpacks a more fundamental code, a cosmic decoding process that transforms a sheet of data into a world of experience. But what is this data? What is the code? Is it bits? Is it geometry? Is it thought? Some physicists, like Eric Verlinde, have proposed that gravity itself is not a fundamental force, but an emergent phenomenon, an entropic effect that arises from changes in the information content of space. In this view, gravity is not a pull. It is a gradient of knowledge, a consequence of how the universe reorganizes itself to preserve informational balance. And if that is true, then we live not in a universe of things but in a universe of correlations, a universe where every event is a message, every interaction is a recalibration, every force is a compression of uncertainty. This may sound abstract, but it has real implications, because if space is not fundamental, then the quantum entanglement between particles, the strange connection that allows instant correlations across vast distances, may not be spooky at all. It may simply reflect the deeper unity of the underlying information. In this view, the separation we perceive between things is not absolute. It is a mirage, a byproduct of decoding. Like the apparent depth in a hologram, created not by distance but by interference. And that brings us to consciousness. If reality is a hologram, and if the physical world emerges from information, then perhaps mind is not confined to the brain. Perhaps awareness is not an isolated phenomenon, but a ripple in the deeper structure of the hologram itself. Perhaps the observer is not separate from the observed. Perhaps the act of seeing is an act of participation. Perhaps what we call reality is incomplete without the presence of mind. This is not to say that the universe is a dream, or that physics is fantasy. It is to say that the more we learn, the stranger the truth becomes. That the closer we look, the more reality dissolves into questions. Is the universe a hologram? We do not know, but the mathematics suggests a hidden symmetry. The physics hints at a deeper correspondence. The information behaves in ways that cannot be ignored. And so we ask, not because we doubt the real, but because we trust that every layer we uncover brings us closer to something more profound. Chapter 19. What happens inside a black hole? There is a place where space folds in on itself so violently that not even light can escape its grip. A region of the cosmos so extreme, so singular, that it defies not only the forces of nature but the logic we use to describe them. We call this place a black hole. But that name is far too simple, far too silent, to reflect the storm of paradox and power that rages at its core. For inside a black hole, space is not space, time is not, and the fabric of reality as we know it unravels thread by thread into something that challenges the meaning of existence itself. To understand what happens inside a black hole, we must first accept that the rules we live by, rules of motion, of direction, of cause and effect, begin to dissolve the moment we cross its invisible threshold, the event horizon. This is not a wall in the traditional sense. There are no alarms, no flashes of light, no dramatic transitions. To someone falling inward, nothing seems different at first. But from the perspective of an outside observer, the fall never completes. The infalling object slows, fades and freezes at the horizon, forever denied the descent. And yet, from the viewpoint of the one falling, the journey continues, inevitably, unstoppably, into the heart of darkness. The closer one gets to the singularity, the more distorted everything becomes. Space contracts, time dilates, directions lose their meaning, up and down collapse into radial inevitability. All motion is drawn inward. Even photons, those swiftest of messengers, cannot find a path outward. There is no turning back, there is no stopping, there is only falling, forever falling, toward a point where the known laws of physics begin to contradict themselves. At the center of a black hole lies what is called the gravitational singularity, a region of infinite density where our equations break, not due to a flaw in the universe, but due to the incompleteness of our understanding. At the singularity, space becomes so curved, so compressed, that its geometry is no longer meaningful. The very idea of distance collapses. Mass becomes infinite, volume becomes zero, and time ceases to be a dimension that can be measured. All paths, all futures, all possibilities converge into a point of unknowable fate. And yet, we do not know if this singularity is real in the physical sense, or merely a placeholder in our mathematics for something we cannot yet describe. What lies inside a black hole is not just a question of astrophysics, but a question of ontology, of what it means to be real, to exist, to be located somewhere. For how can we speak of inside when no signal can leave, when no map can be drawn, when no observer can report back? In the classical description offered by general relativity, the singularity is the end of the line, not just the end of a journey, but the end of space, the end of time, the end of meaning. But quantum theory refuses to be so final. It demands that information cannot be destroyed, that unitarity must be preserved, that even the death of a star must still obey the laws of logic that govern all transformation. This tension between relativity and quantum mechanics reaches its most violent expression in the black hole interior. It is here that the need for a theory of quantum gravity becomes undeniable, for only such a theory could resolve the paradoxes that emerge when space-time itself begins to fall apart. One possibility is that the singularity does not exist in the way we imagine it, that before the laws collapse, a new regime of physics takes over, a quantum foam, a loop of geometry, a string of vibration, that instead of a point, there is a process, a transition, a passage not to nothingness, but to something else, perhaps another region of space, perhaps another universe, perhaps a rebirth. Some theories suggest that what lies beyond the singularity is a white hole, the time reverse of a black hole, a region that only expels matter and never allows anything in. In this view, matter falling into a black hole could emerge elsewhere, else when, in a cosmic rebound that turns collapse into expansion. Could this be what gave rise to our own Big Bang? Could every black hole be the seed of a new cosmos? Others propose that the interior of a black hole is not a singular point, but a vast internal landscape, a kind of hidden universe folded into a finite volume from the outside, but infinite from within. If true, then what falls into a black hole does not die. It enters another world. Still others speculate about wormholes, tunnels through space-time that connect distant regions. Perhaps the center of a black hole is not an end, but a bridge. Perhaps what appears as death from one side is a doorway from another. But these models raise more questions than answers. Can a wormhole remain stable? Can it transmit information without destruction? Can travelers survive the passage? Can time flow coherently on both sides? All of these ideas are speculative. All lack the clarity of direct evidence, but they speak to our unwillingness to accept finality, to our hope that no path truly ends, to our belief that even in the deepest gravity, something remains. There is another strange idea, perhaps stranger than all the others. It comes from the intersection of quantum mechanics and thermodynamics, and it concerns the black hole's entropy. According to Wittgenstein and Hawking, the entropy of a black hole is not proportional to its volume, as one might expect, but to the surface area of its event horizon. This suggests that all the information about the interior is encoded on the boundary, the horizon itself. This leads to the holographic principle, which proposes that the entire interior of a black hole is a kind of projection, an emergent phenomenon that arises from information stored on the surface. If this is true, then the inside of a black hole is not a place at all. It is a calculation, a compression, a narrative inferred from the surface. And if that is true of black holes, perhaps it is true of the universe itself. Perhaps what happens inside a black hole is not merely the collapse of matter, but the collapse of assumptions, the implosion of certainty, the end of place, and the beginning of pattern. Perhaps the singularity is not an object, but a limit, a boundary of what we can know, what we can say, what we can measure. But even with all of these possibilities, we are still left with one undeniable fact. No one has ever seen the inside of a black hole. No probe has returned. No image has resolved its core. The best telescopes can trace the glow of matter on the edge. The best simulations can predict the paths of falling stars. But the truth, the interior, remains cloaked. And perhaps that is its purpose. Not to be understood, but to be approached. Not to be revealed, but to be imagined. Not to be conquered, but to humble us. Because in that darkness lies the ultimate mirror. In that silence, the purest question. What happens inside a black hole? What happens when knowledge ends? Perhaps one day we will know. Perhaps not. But the asking, the wondering, the refusing to stop imagining, that is the light we carry into the void. Chapter 20. Can information ever be truly destroyed? There is a principle, subtle and yet sacred, that flows through every corner of science, like a quiet oath sworn by the universe itself. That information is never truly lost, no matter what changes form, no matter how chaos creeps in, no matter what gets burned, broken, shattered, or swallowed. Something essential, something measurable, something knowable always remains. And yet, standing at the edge of one of the greatest mysteries in all of physics, this sacred principle begins to tremble, because black holes, those enigmatic furnaces of gravity, pose a question that rattles the foundation. What happens to information when it falls inside? Imagine a book, a single volume, filled with words, names, events, and meaning. Burn that book, and the pages crumble. The ink vanishes into flame. But if you're careful enough, if you gather every wisp of smoke, every spark of light, every molecule that drifts upward, in theory you could, with perfect knowledge and infinite patience, reconstruct every sentence that once was written. This is the promise of quantum mechanics, unitarity. That evolution is reversible. That information, however disguised, is conserved. That nothing is ever truly erased. But now imagine that same book thrown into a black hole. No light escapes, no signal returns. The event horizon seals the contents, and eventually, according to Hawking's discovery, the black hole begins to evaporate. It emits thermal radiation, random, chaotic, unstructured. No imprint of the book remains, no whisper of its sentences, no echo of its ideas. Just heat, just emptiness, until the black hole vanishes altogether. What then? Where did the information go? This is the heart of the black hole information paradox, a clash between the laws of quantum mechanics, which demand information conservation, and the predictions of general relativity, which offer no path for that information to escape. For decades, this puzzle remained one of the most unsettling in theoretical physics. If black holes destroy information, then quantum theory, our most precise and successful framework, must be incomplete or wrong. But if information survives, then something about black holes, something beyond the horizon, something not visible, must preserve it. One idea suggests that information is not lost, but scrambled, that Hawking radiation, though seemingly random, contains subtle correlation. Like an encrypted message, its pattern is unintelligible to us, but not meaningless. Over time, perhaps, every bit of information that fell in is encoded in the radiation that comes out. But how? If information cannot escape from within the horizon, then where is it stored? This is where the holographic principle emerges again, suggesting that the boundary of a black hole, its event horizon, acts like a storage device, that the surface area, not the interior volume, encodes the information, that everything that falls in is smeared across the horizon, waiting to be unraveled by future radiation. This leads to bold and bizarre proposals. Some suggests that the interior of the black hole is a kind of illusion, that the true physics lies entirely on the surface, and what we imagine as depth is an emergent projection. Others invoke firewalls, hypothetical walls of high-energy particles that form at the horizon to destroy falling information in a way that is still somehow recoverable. Still others look to quantum entanglement, suggesting that the radiation and the remaining black hole are linked in such a way that total information is preserved, though split across unreachable domains. Each theory attempts to save the central promise that the universe does not forget, that the ledger is never erased, that what is true once known remains knowable. But this leads us beyond physics, into philosophy. What is information? Is it a physical thing? A pattern? A potential? Is a thought once thought eternal? Is a choice, once made, woven into the cosmos? Or is information like a dream, real while present, but gone once you wake? Some physicists believe that information is the most fundamental currency, more basic than matter, more enduring than energy. In this view, reality is not built from particles, but from relationships, from distinction, from differences, from the yes and no of binary logic, the bits that underlie the fabric of space and time. And if that is true, then information is sacred. It cannot be made or destroyed, only moved, only transformed, only translated. This belief has given rise to entire fields: quantum information theory, quantum computing, entropic gravity, that treat information not as a descriptor, but as the thing itself. And yet, there is still doubt. What if black holes do destroy information? What if the final whisper of a thought, once swallowed by gravity, is gone forever? What if memory can be erased, not just in minds, but in matter? Would the universe unravel? Would entropy increase in ways we cannot repair? Or would it simply mean that the map we use is too limited, that we must rewrite the laws to make room for silence? Some propose that information is lost in another dimension, that what disappears from our space is preserved elsewhere, in a shadow universe or a quantum remnant. Some say that wormholes, linking black holes across space or time, carry the information secretly away. Others propose that at the Planck scale, where gravity and quantum mechanics merge, new laws await, laws we do not yet understand, but which rescue the sacred principle in ways we cannot yet imagine. And all of this raises a deeper, more personal question. If information can never be destroyed, then what of you? Are your thoughts eternal? Are your choices permanent? Is there a cosmic record, not of atoms, but of awareness? And if so, then perhaps nothing is ever truly lost. Not a memory, not a moment, not a self. Perhaps you are written into the fabric of space. Perhaps your life, your light, your laughter are all preserved, somehow, somewhere, in the holographic library of everything that has ever been. And if information can be destroyed, then perhaps the universe forgets, and forgetting, perhaps, is a kind of grace. Chapter 21. Are parallel universes real? There is something unsettling and yet strangely beautiful about the idea that the universe, vast as it already is, might be only one of many, that this existence, the one we touch, remember and breathe inside, could be a single thread in an unimaginably vast tapestry, where every possible version of reality is woven side by side, silently unfolding beyond reach, beyond knowing, but not beyond reason. The idea of parallel universes is not merely a sci-fi curiosity or a poetic metaphor. It has slowly and steadily found a foothold in the very fabric of scientific theory. It begins, as so many cosmic questions do, with quantum mechanics, that elegant, elusive system of rules that governs the subatomic world. At the core of quantum theory is the idea of superposition, that a particle does not exist in one state, but in all possible states at once, described by a wave function that encodes every potential outcome. But when we observe the system, that wave function appears to collapse. One outcome becomes real. The others vanish. Or do they? In 1957, physicist Hugh Everett III proposed a radical idea. What if the wave function never collapses? What if, instead, every possible outcome of a quantum event actually occurs, but in a different branch of the universe? What if, each time a particle chooses a path, the universe splits into multiple non-communicating versions, one for each possible result? This is the many worlds interpretation. And if it is true, then reality is not singular. It is pluripotent. It is branching. It is endless. According to many worlds, every quantum event spawns a new universe. When you flip a coin, one version of you sees heads, another sees tails. When a star explodes, every possible configuration of its particles becomes real somewhere. When you make a choice, you don't abandon the alternative. You live both. In parallel. These universes do not communicate. They do not interact. They are not stacked like layers or floating like bubbles. They exist in a vast and growing configuration space, a mathematical realm of outcomes. They are real, but unreachable. You cannot jump from one to another. You cannot look across the veil, but they are there, if the theory is correct. This idea, as bizarre as it sounds, is consistent with the mathematics of quantum theory. It explains the probabilistic nature of measurements without invoking mysterious collapses. It restores determinism to physics. Every event follows from the evolution of the universal wave function. Nothing is random. Nothing is destroyed. Everything that can happen does happen. But is this reality, or is it mathematics masquerading as truth? Many physicists accept the many worlds interpretation as elegant and eternally consistent, but others find it extravagant, wasteful, philosophically disorienting. If there are infinite versions of you, each living out every conceivable variation of your life, Then what does it mean to be you? Where is meaning? Where is responsibility? Where is choice? These are not questions physics can answer, but the theory demands we ask them. And quantum theory is not the only path to the multiverse. Cosmology, too, points to a vastness beyond comprehension. According to the theory of cosmic inflation, our universe underwent a rapid and exponential expansion in the earliest fraction of a second after the Big Bang. This inflation was not a one-time event. It could be eternal. In some regions of space, inflation may end, allowing matter and galaxies to form. In others, it continues. The result is a multiverse, a sprawling collection of bubble universes, each with its own physical constants, its own laws, perhaps even its own dimensionality. In some of these universes, gravity might be weaker. In others, stars may never form. In still others, chemistry may be impossible, or time may behave differently. Our universe, with its precise balance of forces that allows for life, may be only one oasis in a cosmic desert of variation. This is the cosmological multiverse, and it arises not from fantasy but from the mathematics of inflationary models. It is not proven, but it is consistent with what we know. There is also the brain multiverse, emerging from string theory, a framework that proposes that all particles are tiny vibrating strings, and that our familiar three-dimensional universe may be a brain floating in a higher dimensional space. Other brains, other universes, may float nearby, occasionally brushing against ours, perhaps even influencing events through gravity or other forces that leak between dimensions. And then there is the mathematical multiverse, a truly radical idea proposed by Max Tegmark. It suggests that every mathematically possible universe exists, not just as a thought but as a reality. If a consistent set of physical laws can be written, then somewhere, somehow, that universe exists. Our universe is just one point in the vast space of logical possibility. Each of these multiverse theories arises from a different domain of science: quantum mechanics, cosmology, string theory, mathematics, and yet they converge on a single unsettling idea that what we call the universe may not be the universe at all. It may be a local condition, a branch, a bubble, a page in a book we will never finish reading. But if parallel universes are real, what does that mean for us? Does it mean that every version of our lives exists, that there is a world where you never left, where you never arrived, where everything turned out differently? Is there comfort in that thought, or horror? Are we alone in this version of ourselves, or eternally accompanied by the shadows of choices we did not make? And yet, for all the metaphysical weight these questions carry, there remains a deeper, stranger point, that the existence of other universes might help explain this one. Why are the laws of physics so finely tuned? Why does the universe allow for complexity for life, for mind? One answer is that it doesn't need to. In a multiverse of endless variation, there are bound to be some universes where the conditions are just right, and we, by necessity, live in one of those. This is the anthropic principle, the idea that the universe appears fine-tuned, not because of design, but because only in such a universe could we exist to ask the question. It is not a satisfying answer. It feels like a shrug, but it may be true. And truth does not always flatter the heart. So, our parallel universe is real. We cannot observe them directly. We cannot measure them. But the equations we use, the theories we trust, the patterns we see, all of them point toward a reality that is larger, deeper, and stranger than we once believed. And if these universes exist, then perhaps we are not singular beings, but multidimensional echoes. Not a single voice, but a choir. Not a story, but a library. And perhaps in some unfathomable way, we are not limited to this life alone. Not bound to one path. Not confined to one fate, but part of something far greater. A cosmic chorus of possibilities, all singing at once. Chapter 22. Can the future influence the past? We live in a universe that moves forward, or so we believe. The ticking of clocks, the graying of hair, the falling of leaves, the passing of breath. All of it seems to point in one direction, from past to present, from present to future, from what was to what is, to what might become. Time, in this framework, appears as an arrow, simple, straight, and irreversible. But beneath this familiar rhythm, beneath the human story we map onto every hour, there is a deeper strangeness, a riddle that defies logic, yet remains embedded in the laws of physics themselves. Is it possible that the future can influence the past? The question sounds like heresy. It offends our intuition. We are used to thinking of causes leading to effects, of reasons preceding results. We do not expect to see footprints before the feet land. We do not expect to feel hunger before the food is gone. We assume the past is fixed, permanent, untouchable. And yet, at the very foundation of our understanding of the universe, the distinction between past and future begins to blur. In quantum mechanics, the laws that govern particles at the smallest scales are time-symmetric. This means the equations that describe their behavior work equally well whether time is moving forward or backward. The evolution of a quantum wave function is not bound to a direction. It does not care what we call before or after. In fact, the mathematical structures that govern particles often treat time as just another coordinate, like space, not as a flowing stream, but as a dimension in a static landscape. And yet we perceive time as something that flows. We observe events unfold in a sequence. We remember the past. We do not remember the future. This perception is rooted not in the equations, but in the conditions. The universe we live in began in a state of low entropy, and entropy has been increasing ever since. This gives rise to what we call the arrow of time, a direction that emerges not from the laws themselves, but from the particular way those laws are applied to our universe. But what if the arrow of time is not absolute? What if in some hidden structure, time is not a one-way path but a two-lane road? In recent years, physicists have begun exploring interpretations of quantum theory that challenge our classical assumptions about causality. One such idea is retrocausality, the possibility that effects can precede their causes. That what happens in the future can somehow influence, determine, or constrain what happens in the past. This is not science fiction. It is not an attempt to build a time machine. It is a serious attempt to resolve the paradoxes that arise in quantum experiments. Paradoxes that cannot be explained by ordinary forward-in-time reasoning alone. Consider the delayed choice quantum eraser, a thought experiment first proposed by physicist John Wheeler, and later realized in laboratory settings. In this experiment, a photon is sent through a pair of slits, and then detected on a screen, much like the classic double-slit experiment. But after the photon has passed the slits, the experimenter chooses whether to measure which slit it went through, or to erase that information. Astonishingly, the pattern on the screen depends on that later choice. If which path information is preserved, the interference pattern disappears. If the information is erased, the interference reappears, even though the decision to erase was made after the photon had already passed through the slits. This seems to suggest that a measurement made in the present affects the behavior of a particle in the past. Some physicists explain this by invoking entanglement and non-locality, but others argue that the best explanation involves a reversal of causality, a kind of temporal non-locality, where events in time are as connected as events in space. In two-state vector formalism, developed by physicists Jacques Aharonov and Lev Weidman, quantum systems are described not only by a wave function evolving from the past to the future, but also by a wave function evolving from the future to the past. In this framework, what we observe in the present is determined by boundary conditions, both in the past and in the future. The universe is not driven only by initial causes, but also by final outcomes. This is a radical shift in perspective. It suggests that the present is not simply the result of the past, but also a preparation for the future, that the entire fabric of time is interwoven, that the universe is in some deep way self-consistent, not built from a cascade of causes, but from a timeless, all-at-once configuration. And if this is true, then perhaps our deepest assumptions about time are wrong. Perhaps the future already exists. Perhaps it is as real as the past. Perhaps we are not moving through time at all, but revealing its layers. In block universe theory, inspired by Einstein's relativity, time is treated as a dimension in a four-dimensional space-time. The past, present, and future all coexist. They are equally real. Our experience of now is not a universal truth, but a feature of consciousness, a moving spotlight illuminating one slice at a time. If time is a block, not a river, then causality is not a force that pushes us forward. It is a pattern we perceive, a way of making sense of our slice. In such a framework, influencing the past becomes meaningless. Everything that has happened, is happening and will happen, is already embedded in the structure. We are not changing the past, we are participating in a configuration that includes all of it, already. But even if time is fixed, we still experience agency. We still make choices. We still struggle with regret and hope. So the question returns not only to physics, but to philosophy. If the future can influence the past, what does that mean for free will? What does it mean to choose if our actions are already encoded in a timeless structure? What does it mean to be responsible if our outcomes are part of the pattern? And yet there may be a deeper freedom, one not tied to control but to coherence. Perhaps we are not puppets pulled by the future. Perhaps we are co-authors of the story. Perhaps time is a dialogue, not a monologue. A resonance, not a command. In some interpretations, the universe is a kind of computation, a system processing information, exploring all possibilities, collapsing into consistency. And in this view, the future does not force the past, but clarifies it. Each moment updates the whole. Each observation refines the state. The present is not merely downstream from the past, it is also upstream from the future. And in that middle place we exist, not as isolated agents, but as collaborators with time itself. We are not merely living from cause to effect. We are participating in a conversation between what was and what will be. And perhaps that is the true mystery, not whether we can influence the past, but whether the past and future are already speaking through us. Chapter 23. What is nothingness made of? There is something haunting in the silence between stars, in the space between atoms, in the invisible breath that surrounds every object, every motion, every thought. We call it empty. We call it vacuum. We call it nothing. But what if the void is not a void at all? What if the silence is filled with symphony? What if the background of the universe is more alive, more structured, more foundational than the things we place upon it? This is not a question of philosophy, though it is as old as human thought. It is a question of physics, and the answer is stranger than we ever dared imagine. To understand what nothingness is made of, we must begin by stripping away everything we know. Remove the planets, erase the stars, dissolve the clouds of gas and dust, silence the radiation, scrub away every particle of matter, every flicker of light. We are left, we believe, with emptiness, a pristine vacuum, devoid of form or content. But even then the void is not still. In the quantum world, even the most perfect vacuum is seething with activity. According to the principles of quantum field theory, every point in space is filled with fields, fields that exist even in the absence of particles. These fields cannot be truly at rest. They fluctuate. They shimmer. They buzz with the energy of uncertainty. This is the result of the Heisenberg uncertainty principle, which tells us that certain pairs of properties, like energy and time, cannot both be precisely known. And so, even in a perfect vacuum, energy must fluctuate. Particles and antiparticles flicker into existence and annihilate one another in timescales too short to observe. This is not metaphor. This is measurable. These vacuum fluctuations have real consequences. The Casimir effect, for example, demonstrates that two uncharged metal plates placed extremely close together in a vacuum will experience a measurable force pulling them together, not because of any particle between them, but because the quantum fluctuations outside the plates differ from those inside. The vacuum has structure. The vacuum has pressure. In this sense, the vacuum is not empty space. It is a dynamic medium, a ground state, a lowest energy configuration of all fields that fill the universe. It is not a container. It is a participant. In fact, the vacuum might be the most real thing there is, because even the particles we observe, electrons, quarks, photons, are not fundamental things, but excitations of the underlying fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. The vacuum is what remains when there are no ripples, but it is never truly still. So we must stop thinking of nothingness as absence. It is not the lack of being. It is the ground of becoming, and it holds secrets. Perhaps the most staggering of these secrets is revealed when we ask about energy. If the vacuum is filled with quantum fluctuations, then it has energy. Vacuum energy. But how much? The equations suggest an enormous value, so large that it would cause the universe to expand violently. But that does not happen. In fact, when we compare the calculated vacuum energy with the observed expansion of the universe, attributed to dark energy, the numbers disagree by 1,120 orders of magnitude. This is the cosmological constant problem, one of the greatest unsolved puzzles in physics. It is as if the vacuum is filled with energy we cannot measure, yet that energy somehow nearly cancels itself out, leaving behind a whisper, a gentle push that accelerates the expansion of space. That whisper is dark energy, and it arises not from things, but from the vacuum itself. So what is the vacuum? Is it a field, a code, a computational substrate? Some physicists suggest that space itself is emergent, that the vacuum is not a passive backdrop, but a quantum entangled network, a vast web of informational relationships that gives rise to geometry, motion, and time. In this view, the vacuum is not where things happen. It is how things happen. It is the stage. It is the script. It is the logic beneath the surface. Others go further. In theories of quantum gravity, such as loop quantum gravity, space is not continuous. It is quantized. The vacuum is made of discrete units, like pixels on a screen, each representing a tiny chunk of volume, far smaller than any particle. These units form a granular, foamy texture at the smallest scale. What we perceive as smooth emptiness is, at the Planck scale, a storm of loops, connections and spins. The vacuum is not flat. It is woven. And in string theory, the vacuum is not unique. There are countless possible configurations of the underlying strings and brains, each one corresponding to a different version of physics. The vacuum state is not a single solution. It is a vast landscape with valleys and hills, each defining its own universe. We live in one valley. There are others. The vacuum, then, is not one thing. It is a multiverse of possibilities. But no matter the theory, one truth emerges: there is no such thing as true nothingness. Every attempt to find it reveals more structure. Every effort to erase content reveals deeper content. Even in the coldest regions of intergalactic space, where no atoms drift, where no light shines, the vacuum teems with virtual particles. Even in the most carefully prepared lab, the vacuum resists perfect silence. It hums with the music of possibility, and perhaps most haunting of all, the vacuum may be unstable. Some models suggest that the vacuum state we occupy is not the lowest possible energy configuration, that we live in a false vacuum, a local minimum, a metastable state. If this is true, then the universe could someday tunnel into a lower energy vacuum, triggering a phase transition that would rewrite the laws of physics. The very fabric of space could change, wiping away atoms, stars and minds, in a bubble of catastrophic renewal. This is not science fiction. It is a natural consequence of quantum theory applied to cosmology. If the vacuum can change, then it has a history. If it has a history, then it is not nothing. It is a field, a phase, a presence. And so we return to the question, what is nothingness made of? The answer is both simple and profound. Nothingness is made of everything, of potential, of symmetry, of fluctuations, of rules that never rest. It is not a void, it is a mirror in which we see not our absence, but our foundation. We came from the vacuum, we are made of its ripples, and when we return to dust, we return to it, not to emptiness, but to the source. Chapter 24. Does the universe have a mind? There is a quiet wonder that overtakes us when we stare too long into the night sky. Not the kind of wonder born from curiosity alone, but the kind that echoes back from within. As though the universe is not just something we observe, but something that observes us in return. The constellations shine not just with distance and light, but with a strange familiarity, as if their silence knows something we have not yet asked. It is in this silence that a profound and unsettling question begins to form, not a scientific hypothesis, nor a spiritual declaration, but a whisper born of both. Does the universe have a mind? The question at first glance feels absurd, almost childish, an echo of the earliest myths in which stars were gods and storms carried messages. But peel back the symbols, strip away the poetry, and the question remains, not as superstition, but as speculation at the limits of science, philosophy, and consciousness itself, because what we call a mind is not merely a brain, it is a pattern, a dynamic structure of self-reference, of feedback, of awareness. And if that pattern can arise from matter, if neurons and electrons and chemicals can conspire to produce reflection, thought and will, then what stops such a pattern from arising on a scale far greater than the skull? To ask if the universe has a mind is not to ask if it thinks like we do. It is to ask if thought, whatever its form, is an emergent property of complexity, and if so, whether the totality of all things might possess, somewhere deep in its structure, some flicker of cognition, some whisper of perception. In our own brains, consciousness emerges not from any single part, but from the interaction between billions of parts. Neurons fire, synapses link, signals move in loops and waves and spirals. There is no single command center, no throne of the self. The I we speak of is a process, not a point. It is the result of integration. Now imagine the universe in similar terms. Galaxies as neurons, gravity as connection, quantum fields as energy flowing through vast circuits of matter and time. The structure of the cosmic web as revealed by deep sky surveys shows a pattern that bears a curious resemblance to neural networks. Filaments of dark matter thread between clusters of galaxies, forming nodes and pathways, voids and hubs. It is not proof of anything, but it is a metaphor that will not let go. Could this structure process information? Could it generate feedback? Could it, over unimaginable time, develop awareness. This is not mysticism. It is a line of reasoning rooted in physics, in complexity theory, in system science. We know that systems can become self-aware. We are proof. We are matter that became aware of itself. We are the universe looking back at itself through the lenses of eyes and thought. If the laws of nature allow for this at the scale of a human brain, then why not at the scale of the cosmos? Some scientists propose that consciousness is not something that emerges at a certain level of complexity, but something that is fundamental, woven into the fabric of existence. This is known as panpsychism. The idea that all matter has some form of proto-consciousness, that experience is a basic feature of the universe, not an afterthought. In this view, just as space and time are fundamental dimensions, so too is mind. This does not mean that rocks think, or that atoms have opinions. It means that experience in some form exists along a continuum, from the dim awareness of a particle's location, to the rich symphony of human introspection, to potentially even the cosmic scale awareness of the universe itself. It is a view that stretches our definitions, but not our logic, and it leads to another radical possibility, that consciousness and the universe are not separate things, but aspects of the same underlying reality. That what we call matter and what we call mind are two faces of one thing, like temperature and energy, like wave and particle. This idea finds echoes in quantum mechanics, where the role of the observer seems inextricable from the nature of the observer. In some interpretations, such as the participatory anthropic principle, consciousness is not a passive recipient of the universe, it is an active player in shaping it. Reality does not become definite until it is measured. And measurement in this context involves awareness. Could it be that the universe requires observation to become real? And if so, then who or what observes the universe as a whole? If consciousness is required for reality to manifest, and if we are not the only conscious agents in the cosmos, then perhaps consciousness is not a latecomer to the story, but the story itself. Some physicists propose that the universe is a kind of computation, not metaphorically, but literally. That the fabric of space and time is discrete, that the rules it follows are algorithmic, that reality is a vast quantum computation unfolding in cosmic time. If this is true, then perhaps consciousness is the output of that computation, or perhaps it is the computation itself, looping back upon itself in recursive awareness. There is also the idea that the universe is a self-similar fractal, containing patterns that repeat across scales. If so, and if consciousness emerges at one scale, it might emerge at others. The universe might be conscious not in spite of its vastness, but because of it. The more parts there are, the more connections there can be, the more feedback, the more awareness. And yet, for all this speculation, there is no proof. There is no telescope that can detect awareness. There is no equation that can describe the qualia of a cosmic mind. But the absence of proof is not proof of absence. It is an invitation to wonder. Because to ask whether the universe has a mind is ultimately to ask whether our minds are alone, whether the sense of mystery we feel when we contemplate the cosmos is merely projection or recognition. It is to ask whether the voice we hear in silence is ours, or a whisper from something deeper. And it is to confront the possibility that the universe is not a machine, not a cold expanse of blind forces, but a being, a presence that includes us, not just as particles, but as thoughts. If that is true, then perhaps we are not observers of the cosmos. We are neurons in its mind. We are dreams in its sleep. We are stories it tells itself. And consciousness is not a candle in the dark. It is the light by which the dark becomes visible. Chapter 25. Will we ever know everything? There is a hunger stitched into the human soul, a relentless, aching urge not only to survive, not only to understand a single moment or a single place, but to comprehend the whole of it, to reach past the veil of mystery and grasp the full shape of reality, not in fragments or fleeting glimpses, but entirely, from the mechanics of atoms to the breath of galaxies, from the mind's silent voice to the boundaries of time itself. We have always asked, can we know it all? Is it possible through thought, through math, through trial and persistence and vision, to unlock every truth the universe holds, and look upon existence with nothing left hidden? In other words, will we ever know everything? To ask such a question is to step into the storm, because it is not only an inquiry about science or knowledge, it is a challenge to the very nature of limits. It requires us to examine the walls around our understanding and ask whether those walls are temporary shadows or permanent barriers. It demands that we look not just at what we know, but at what knowing means. Science, for all its power, is not a light that shines uniformly. It flickers, it leaps, it stumbles forward through generations. Each answer leads to more questions, and even the clearest theories open new doors to darkness. Newton gave us motion. Einstein gave us relativity. Quantum mechanics opened up the microscope. But every revolution in thought, rather than closing the book, writes new chapters that our minds can barely begin to read. One of the most humbling truths in physics is that our current understanding, despite its precision, despite its elegance, is incomplete. The laws that govern the very large and the very small refuse to unite. General relativity, which describes gravity and spacetime, clashes with quantum mechanics, which rules the atomic and subatomic. We have two masterpieces, but they speak different languages. A theory of everything has remained elusive, not for lack of effort, but perhaps because the very nature of reality defies being captured by one single theory. And even if we do find it, some unified description, some perfect equation that explains every force, every particle, every interaction, would that be enough? Would knowing the code mean we understand the story? There are deeper constraints than complexity. There are limits built into the very framework of logic and mathematics. In 1931, Kurt Gödel proved a result that still echoes like thunder through the halls of reason. In any sufficiently powerful formal system, there will be true statements that cannot be proven within that system. This is not a failure of our tools, it is a feature of logic itself. There will always be truths beyond reach, always propositions that can be conceived but never resolved. This is not merely about math. It is about knowledge. If even our most precise languages are incomplete, how can we hope to encapsulate all that is? Then there is Heisenberg's uncertainty principle, which tells us that we cannot know both the position and momentum of a particle with perfect accuracy. The act of measuring one disturbs the other. This is not a limitation of instruments, it is a limitation of the universe. There is a fundamental fuzziness at the heart of nature, and no matter how clever we become, no matter how powerful our machines grow, this fuzziness remains. The deeper we look, the more the act of looking changes what we see. So what, then, does it mean to know everything? Is it the ability to predict all future events? Is it the possession of a final theory? Is it the mastery of all causes and effects? Or is it something subtler? Some believe that we are approaching a kind of knowledge asymptote, that our understanding is climbing ever higher, but will never reach the summit, that we are trapped within our biological limits, within the narrow window of human cognition. We evolved to survive, not to comprehend the infinite. Our brains are finite, our perception is filtered, our metaphors are rooted in the familiar. Perhaps there are truths that simply cannot fit inside us, but must all knowledge be conscious? Could there be ways of knowing that are not linguistic, not symbolic, not bound to reason as we define it? Could a future mind, a synthetic intelligence, or an evolved consciousness grasp truths that are invisible to us, not because they are secret, but because we lack the architecture to perceive them? In the vastness of the unknown, perhaps the question is not will we ever know everything, but who is the we that asks? Because the universe is not waiting to be understood. It is what it is, regardless of our comprehension. And in that sense, everything is already known by the universe to itself. Perhaps knowing everything is not about possession, but participation, not about storing all facts, but standing in harmony with all truth. There is also the question of meaning. What would it mean to know everything? Would we feel peace or paralysis? Would curiosity die? Or would it become wonder without edge? Because knowledge is not simply the accumulation of data, it is the dance between question and answer. It is the hunger that pulls us toward mystery. If we reach the end, would we still ask? Would we still grow? Would we still live in the same way? And perhaps this is the deepest thought of all. Perhaps the unknowable is necessary. Perhaps mystery is not a defect of reality, but the space in which consciousness breathes. Perhaps we were never meant to know everything. Perhaps we are meant to forever approach it, to orbit it, to reflect it, to become it imperfectly, beautifully endless. Because the moment we know everything, we may cease to be the ones who ask. And in the asking, in the reaching, in the never-ending ascent, we become something more, not masters of the universe, but mirrors of its unfolding, not gods of knowledge, but vessels of wonder. And that, in the end, may be the closest we ever come to knowing everything, not by grasping it, but by being a question that never ends.